Hey everyone, welcome to Practically. We bring learning alive. Today I am going to cover a chapter called Coordination Chemistry in our one-shot series. See, this chapter is extremely important not only for your CBSE exam but also for the competitive exam, for example JEE, NEET and whatnot. All those exams, there had been a multiple choice question been asked on this chapter, and not only one or two questions, there had been so many questions. This chapter, you can consider it as a basic of your inorganic chemistry. Just like for organic chemistry, we have a basic called general organic chemistry. You can consider coordination chemistry as general inorganic chemistry. Okay, so on that note, let's begin. So by hearing this word coordination chemistry, what comes to your mind is that coordinate, right? We know there are three types of bond: ionic bond, covalent bond and coordinate bond. So we are going to cover all those compounds, how they are formed, different type of their properties, chemical properties, how do they react, their application and all of that. And those compounds shows or have coordinate bond in them. That is what this chapter is all about. So let's begin. So first, addition or molecular compounds. So what is mean by addition or molecular compound? See, addition of molecular compounds, we're going to see its type also. But before moving to that, let me tell you what it is. Okay, see, you can see here FeSO4 salt solution we have taken. Then you have taken a ammonium sulfate salt solution. Obviously water is with it. You combine it with it, and what do we have got is double salt addition compound. So basically this compound has been obtained. This compound has been obtained by combining the solution of different compound in a stoichiometric ratio. Okay, for example, we have taken FeSO4. Now we don't know how much it is. Okay, it could be, suppose, just a sec. Yes, it could be, it is 1, and it is 6. So this is the ratio 1:1:6. So this is its stoichiometric ratio. So how do this compound has been obtained? See, we take the FeSO4 salt solution, you mix it with ammonia salt solution along with the water. Okay, then you heat it, you let it crystallize. You heat it, you let the water, extra water go, you let it crystallize, and after that you got what? All this compound, that means ammonium sulfate, iron sulfate, all of them have combined together in a particular ratio to give you this compound. That is called as addition or molecular compound. Okay, as far as this example is concerned, it is called as double salt. Okay, and second example, you can clearly see here, copper sulfate is reacting with ammonia. Okay, again this is also being heated. Okay, and crystallization has happened here also. What happened is that you got copper tetraamine sulfate. This is called as copper tetraamine sulfate. That's the compound you have got. Okay, and that is called as coordination compound. The compound you see here is coordination compound. Okay, it is also addition compound. This compound is also addition compound. This compound is also addition compound. But look at the difference. This is double salt. This is coordination compound. And what are those? We are going to see in the next slide. Firstly, you need to understand what is addition or molecular compound. Addition or molecular compounds are the ones which have been obtained by combining solution of a different compounds in a stoichiometric ratio. Then they are allowed to evaporate and crystallize. Then you get the crystals of either a coordination compound like this, or you can get the crystals of double salt. Both of these are addition or molecular compound. Okay, I hope this must have been pretty much clear to you. How do we obtain addition or molecular compound? Now this addition or molecular compounds, they have been divided into two types. One is double salt, another is coordination compound. I know our chapter is coordination compound, but you should understand its brother also. Okay, double salt is nothing but the brother of your coordination compound. Okay, the parent compound is what? Parent compound is addition or molecular compound. It has been divided into two types. One is double salt, another is coordination compound. Okay, now what is the basic difference? See, both this compound, coordination compound as well as double salt, both these compounds have been obtained. Both of these compounds have been obtained by combining a different solution together, allowing them to evaporate, okay, and to form a crystals. Both of them have been obtained in a similar fashion, but there is one basic difference between them. That is what we're gonna see. Double salt. Now, what is double salt? We just do the double salt, right? FeSO4, NH4, 2SO4, 6H2O. This is also called as Mohr's salt. This double salt is also called as Mohr's salt. Okay, now you want to see what's the difference. Okay, till here it's clear, I guess. Okay, how did we obtain this compound? Now let's see. If you put, see, the difference between coordination compound and double salt can only be understood when you try to dissolve or when you put them into water. As soon as you put them in water, let's see what's gonna happen. Excuse me. Okay, firstly we take the double salt. When we put this double salt into water, let's see. Oh, I'm sorry. Okay, we have put this double salt in water. Here you have a water, and let's see what have you obtained. See, whenever you dissolve a double salt into water, whatever ions your double salt is made up of. For example, Fe2 plus is here, SO4 2 minus is here, NH4 2 plus ion is there. So basically, whenever you dissolve a double salt into water, it gets dissociated into its constituent ions, and you can test for those constituent ions anytime. All of these have been dissociated into water. FeSO4 has Fe2 plus, sulfate obviously SO4 2 minus, and NH4 2 plus. This might be a wrong, actually. There's a mistake here. Okay, it is not NH4 2 plus, it is 2NH4 1 plus. Okay, 2NH4 1 plus. So all these ions have got dissociated into water, and if you take a test on them, you will get the test for ammonium ion, you will get a test for ferrous ion, you will get a test for sulfate ion also. Okay, that means double salts, whenever they are dissociated into water, they give all the constituent ions in it. Okay, that's the double salt. Now let's see what is coordination compound. So coordination compound, the very first question, what are they? What is coordination compound? Okay, in coordination compound, see, coordination compounds are a bit different than your double salt. How? See, this is a coordination compound I took. Okay, I put this compound in water. As soon as I put this compound in water, what did I get? This got dissociated as 4K plus FeCN6 4 minus. That means you have got only this cation, and this is your complex ion. This complex ion that you get here, this complex ion does not get dissociated. It does not get dissociated into Fe2 plus 6Cn minus. This does not happen. So in double salt, we came to know that whatever constituent ions, be the cation anions from which double salt was made of, all of those gets dissociated into water, and you can test them for their presence in the solution. But such thing does not happen with coordination compound. Coordination compound maintains their identity in aqueous solution also. That means coordination compound was having K for FeCN6, you get 4K plus FeCN6 4 minus. So even if you try to test Fe2 plus here, even if you try to test a qualitative test for Fe2 plus, you would not get that, because Fe2 plus has been bonded with cyanide only. That is called as complex ion, or it is also called as coordination entity. It is also called as coordination entity. Okay, that is how the main difference between coordinate compound and the double salt is all about. Okay, so this is how the coordination compounds are going to be. Now we're going to see how the coordination compounds are formed, what are different theories behind it. Okay, I hope the picture must have been pretty much clear to you, or let me sort it out once again for you. See, we started with addition or molecular compound. How do we obtain them? You take a salt solution of a different compound, mix them together in water, you allow water to get evaporate. Okay, you let them crystallize, and whatever crystals you get, those crystals are of double salts or coordination compound. So when you get those, you take a double salt and put it into water, you will get the ions from which it was made of. Okay, similarly, if you take the coordination compound and if you try to put it into water, you will not get the ions from which it was actually made of. Okay, previously you have taken Fe2 plus, you have taken Fe2 plus, cyanide and potassium. Okay, before you mix them to form a coordination compound, you can test them for their presence by qualitative analysis. As soon as you mix them, they form a coordination compound, and as soon as they form a coordination compound, your Fe2 plus is bonded with cyanide and it cannot get dissociated that easily by water. Obviously, by heating you can separate it, but I am talking about aqueous medium, so you cannot separate it in an aqueous solution now. That's the main difference between double salts and coordination compound. Okay, since our all focus of this chapter is on coordination compound, we're gonna carry with that now. Okay, so Werner's coordination theory. Now I can directly tell you, okay, I can directly tell you what is Werner's coordination theory and all that. You will understand it also, but I don't want it that way. I want you to see how Werner is the name of a scientist. Okay, I wanted to tell you or feel you how Werner actually reached to his conclusion, and then we're going to see how he proposed a different kind of bondings for its coordination compound. Okay, now you can look at this compound: CO, Cl3, 6NH3, COCl3, 5NH3, COCl3, 4NH3, COCl3, 3NH3. Okay, now let me tell you one thing. That one thing might surprise you a bit. Whenever you put excess AgNO3 into this, so you need to understand this AgNO3 is an ionic compound. Your AgNO3 is an ionic compound. Okay, AgNO3, and it gets dissociated as Ag plus NO3 1 minus, and this Ag plus, it has extra affinity. It has extra affinity for halides. It has extra affinity for halides. Any Ag plus ion would always have an extra affinity for halides. As soon as it sees halides, it will pluck the halides from it. Okay, so that happens here also. See, as soon as you put excess AgNO3 into this, what do you get? You get, see, I'll tell you the structure of this compound later on. Okay, I'm going to tell you the structure of this compound later on, but now what I'm going to tell you is that excess AgNO3, that means you can take as many moles as you want. So as soon as you put it into this, what do you get? From this compound, you get 3 moles 3 moles of AgCl. Now AgCl actually gives you white PPT. Okay, that is why you come to know 3 moles of AgCl. If you put into this compound, you get 2 moles of AgCl. When you put into this compound, you get 1 mole of AgCl. And lastly, when you put into this, you get no PPT. Okay, as far as these 3 are concerned, it gives you white PPT. Now I cannot write the white here, it's because board is already white. That is why I'm writing it in a green color. Okay, so this 3 compound gives you white PPT. Okay, you take this solution of this compound, you take the solution of this compound, you put the AgNO3 into this, excess AgNO3 obviously. As soon as you put the excess AgNO3, this compound gave you 3 moles of AgCl, white PPT. This compound gave you 2 moles of AgCl, white PPT obviously. This compound gave you 1 mole of AgCl, and this compound gave you no PPT. Now, why is that so? Let me tell you one thing that will really surprise you, is that all 4 compounds, if you look at their chemical composition or their chemical formula, is same. Their chemical formula is same. I know it doesn't look like a same here. Their chemical formula, it doesn't look like a same here, I know, but it is same. And it is, well, you can take any compound and I can represent that as its chemical formula. For example, CONH3N ClM. Just a sec, let me take the eraser. Yeah. NH3 X NH3 X Cl Y. What is this? See, all these 4 compounds, they are having ammonia chloride inside this bracket and outside that bracket. I'm going to tell you very shortly what is that bracket is all about. Okay, but before that, let me make you understand that NH3 is inside also, outside also bracket. Chlorine also inside the bracket, outside the bracket. Now that number may vary and is going to vary. Okay, but these are the number N, M, X, Y. Okay, now let's see how a different compound gives different number of PPTs. Okay, I'm gonna leave you with this for maybe 15 seconds for you to perceive and comprehend whatever I have written here. Okay, chalo. Now let's move to the next part, that is valencies. See, what Werner has proposed is that there are 2 types of valency. One is primary valency, another is secondary valency or coordination number. Okay, as per his understanding and whatever experiments he had performed, from that he understood that there are some chloride ions which are getting bonded with He plus to form a white PPT, and there are some chloride ions which are not getting bonded with Ag plus, but they are in the compound. So what's the reason? Okay, from that he understood when he performed a different experiments. Obviously, I mean, there was used to be a test by which you come to know how many moles of Ag cell it actually have formed, whether it's a 1 mole, 2 mole, 3 mole. If there is no PPT, then you can be really sure, okay, that there is no formation of AgCl. Okay, but if there is a white PPT, you need to check it, weigh its mass, and then you can find out how many moles of AgCl it has formed. Okay, now primary valency, secondary valency. What he has understood is that primary valency is just yeah, primary valency is ionizable. It is ionizable, whereas secondary valency is non-ionizable. That means primary valency is actually satisfied by forming a bond with a, primary valency behaves just like a cation and anion. For example, chlorine. If chlorine is to bond ionically with Na plus, you would require only one chlorine. For example, Na plus Cl minus NaCl. Similarly, K plus Cl minus KCl. But if you take a calcium, you will need 2 chloride ions, right? Because calcium valence is 2. So now you form a CaCl2. Similarly, if you take a magnesium, it will form a MgCl2 because valency of magnesium is 2. Okay. Similarly, if you take a aluminium whose valency is 3, so now you will require the 3 chloride ions. So it will give you AlCl3, just like that. Okay. So now here what is happening? The bond between these cations which I just mentioned and the chloride is ionic bond. Okay. It's an ionic bond. So then there is a second type of bond which is a coordinate bond or a coordination sphere, you can say later on. Okay. But for now, what he says that metal shows 2 types of valency. One is primary valency, which is ionizable, and it is generally satisfied by forming a bond with cation or anion only. Primary valency is actually satisfied by forming a bond with a cation or anion. Okay, it cannot be satisfied by forming a bond with neutral species. Okay, and secondary valency, which is also called as coordination number, it can be satisfied by anion, it can be satisfied by neutral ligand, and very rarely it can be satisfied with a cation also. Okay, but the examples are very less. Mostly secondary valency is satisfied by forming a coordinate bond either with a negatively charged species or with a species having lone pair of electrons. Okay, now let's see what are this primary valency, secondary valency. Now you can clearly see here the compound that we took, COCl3, for example, or let me write its structure directly here. It will be quite easy for you to understand that. Okay, so let's take this compound CO. Okay, now it is getting coordinated from 6 sides by NH3. Okay, now these are coordination sphere. Whatever sphere I had drawn is a coordination sphere. Now apart from that, I am going to show you okay, chlorine and chlorine. So here you can easily see, okay, this chlorine has been bonded to your cobalt by primary valency. It is bonded to your cobalt by primary valency, and your ammonia is bonded to cobalt by secondary valency, or you can say that just a sec, this NH3, it is in its coordination sphere. This green color sphere that I am going to draw, it might not be complete exact sphere, but anyways, that is not a point here. So this sphere that you can see, this is called as coordination sphere. Okay, so your ammonia has been bonded with your cobalt in a coordination sphere, and chloride, it's outside the coordination sphere. Chloride, 3 chloride ions are outside this coordination sphere. They are outside. Okay, now whenever you put AgCl into this, now if you put AgCl into this, you will get 3 moles of AgCl. Okay, and if you want me to show you the exact chemical formula of this compound, it would look something like this: CO, NH3, 6 Cl3. Okay, now these 3 chloride ions are outside the coordination sphere, and therefore they are ionizable. Whatever you have outside this coordination sphere, is always ionizable. So this is ionizable. Now if you put the AgCl into this, it will give you 3 moles of AgCl. Okay, now I'll tell you why in that experiment which Werner performed, different compound gave you different moles of AgCl. Okay, now you must have understood that whatever you have inside this coordination sphere would not get ionized, no matter how much AgNO3 you would put. And whatever is present outside this coordination sphere, which is this, okay, you can understand it from here also. Okay, 1, 2, 3, 4, 5, 6, there is a chlorine here also. So it is this. So this chlorine, oh, I chose the wrong color. Okay, so this chlorine, and this chlorine, they are outside the coordination sphere. Just now I show you here also. Okay, now I'm again going to leave you for 15 seconds so that you will understand whatever I had written very clearly. Okay, I hope this must have been pretty much clear to you. Now let's understand this again. Here you have a 6 ammonia ligand inside the coordination sphere, 3 chloride ions outside the coordination sphere. But what if I have a 5 ammonia? Okay, I'll write all the structures here. Now the first one was like this: CO, NH3, 6 and Cl3. So when you put excess AgNO3 into this, it gave you 3 moles of AgCl. Okay, then you took the second compound, CONH3, 5. That means 1 chloride. Now remember one thing: whatever coordination number of a given metal ion is, okay, metal ion atom, whatever, it would always have that coordination number. For example, the coordination number of your cobalt here is 6. So it is going to be 6 anyways. It is going to be 6 anyways and always. So here, out of this 6 ammonia ligand, 1 ligand is not there, only 5 are there. So the 6th coordination number is satisfied by replacing chlorine atom there. Now chlorine comes here. Okay, and what happens? 2 chlorine stays outside, okay, and 1 ammonia ligand also goes outside. Now if you put AgNO3 into this, how many AgCl, how many moles of AgCl are we going to get, you think? We are going to get 2 moles of AgCl because only 2 chlorine atoms are outside. 1 chlorine atom is inside. So whatever ion is present inside this bracket, which is called as coordination sphere, that is not ionizable, non-ionizable. And whatever number of chlorine ions which are present outside this coordination sphere are ionizable. So when you put excess AgNO3, you will get here 2 moles of AgCl. Okay. Thirdly, CO NH3 4. Now 2 chlorine are inside, 1 chlorine is outside. Now since the coordination number of your cobalt is 6, it has been 6, okay, but you need to push 2 ammonia ligands outside. Now you will have 2 ammonia ligands outside. Now even if you put excess AgNO3 here, you will get single mole of AgCl. You will get single mole of AgCl here because only 1 chlorine is outside, okay. And lastly, when you have all the chlorine atom inside the coordination sphere, here Cl3 NH3 3. Okay, now even if I put AgNO3 here, excess AgNO3, you would get no PPD. You would get no PPD. Why? Because there is no chlorine atom outside the coordination sphere, right? All the chlorine atoms are inside the coordination sphere. And as I told you, the atom which is present inside the coordination sphere is not ionizable. So that is how your metal shows 2 valency. One is primary valency, which is this is primary valency, okay, and another is what? Another is your secondary valency, which is here. Secondary valency is nothing but, it is also called as coordination number, and coordination number is a distinct number for a given metal atoms in a given electronic configuration. I know it is obviously going to change as per the electronic configuration, but mostly the coordination number stays same. So that is how the primary valency and secondary valencies are. Okay. Now again, I am going to leave you just for 15 seconds to see all the reactions which I just wrote here. Okay, chalo. Now let's move to some important terms. Okay, these terms are really gonna help you in understanding the chapter in a better way. Okay, now let's see one of those terms. The first one is your central metal atom or ion. Now just now I draw this compound, right? CONH3. It could be 6, it could be 3, whatever it is. Okay, Cl3 here, or you can have K3 Fe and 6, or you can have K4 Fe Cl6. So these are your central metal atom or ion. Okay, sometimes it's neutral, sometimes it is cationic, but it is never anionic. Got this? It is never anionic. So the central metal atom central metal atom is the one which shows primary valency. It is also shows secondary valency, and more often than not it's a D block element only, or sometimes A block also. Okay, central metal atom could be your D block element, or it could be F block element also, and very few times it's a alkaline earth metal also. For example, like calcium, sometimes magnesium, sometimes P block element like aluminium, but those are rare instances. More often than not it's a D or F block element only. Okay, we're going to see that very soon what it is. Okay, sure. Moving ahead, ligands. Now what are ligands? See, ligands are the compounds which are actually forming a bond with your metal atoms. Okay, ligands actually plays the huge role in showing variety of different properties by your given metal atom. Okay, metal atom by itself cannot show variety of different reaction also and property and application also. Okay, it can only be possible if it is bonded with a particular ligand. Okay, so ligands are what? Ligands are basically, if I term them in a technical way, they are nothing but Lewis bases. They are nothing but Lewis bases. Okay, they are electron donors, which Lewis bases are, right? Lewis bases are electron donors only. Now they could be cationic, they could be anionic, they could be neutral also. Cationic, ligand being cationic is very rare instance. More often than not they are either neutral, having lone pair of electrons, or negatively charged ligands. Okay, so ligands are the one which are forming a bond, a coordinate bond or ionic bond with your central metal atom. They are generally Lewis bases, electron donors. Okay, now let's see the classification of your ligand. Okay, the types of ligands. See, there are two types of ligands. Ligands, I'm not saying types, but they can be classified on the basis of a charge or of a basis of denticity. I will come to denticity. What is denticity? Okay, but firstly let's understand it through charge only. Okay, based on charge. So based on charge there are different types of ligands. For example, they could be anionic. What are anionic ligands? Yeah, anionic ligand. Anionic ligands are, let me take the example. For example, halides. All the halides, F minus, Cl minus, Br minus, I minus, then you have a hydroxide, OH minus, NO2 minus. Okay, then you have a cyanide. Cyanide is there. Then you have what? Cyanide, nitro, Cn minus. Any compound having a negative charge. or any species having a negative charge can act as a ligand. Okay, any species having negative charge can act as a ligand. Now, another one is what? The second is your neutral. Neutral ligand. What are your neutral ligands? Neutral ligands are any compound having lone pair of electrons, LPs. Any neutral compound having lone pair of electrons can act as a ligand. For example, compounds having nitrogen in them, okay, compounds having oxygen in them, compounds having sulfur in them. So I'm not going to give you lots of examples. I'm just going to put these atoms at the center. For example, you have ammonia, you have amine RNH2. With the oxygen, you can have a H2O, you can have a alcohol. Okay, with the sulfur, you can have a H2S, like this. So all of these compounds, all of those compounds which are having oxygen, neutral oxygen in them, neutral oxygen, neutral nitrogen, neutral sulfur in them, and sometimes obviously phosphorus also, can act as a ligand because they can donate their lone pair to your central metal atom or ion. Okay, so that is how anionic and neutral ligands are all about. And lastly, I'm going to give you a rare example where ligands can be cationic also. Cationic ligand, and there are very few examples. I'm going to tell you one of them is NO1 plus nitrosyl. It is called as nitrosyl. Okay, so these are the classification of your ligand based on a charge. You can have a look at it. Okay, now that you have understood how the ligands been classified based on their charge, let's see how they are classified on the basis of denticity. Now, denticity is what? See, a given ligand can donate a single lone pair to your metal atom. It can donate a two lone pair from two different atoms. Okay, I mean the ligand is same, the complete compound is same only, but there will be two atoms which would be donating two lone pair to your central metal atom. You need to understand first thing is that every atom in whatever compound you take, can maximum donate one lone pair at a time only. Okay, you would not see any compound where an atom is there which is donating two lone pair at a time. No. Take any compound. If you take a single atom, the single atom you would find always donating a single lone pair. There can be two different atoms which are donating two lone pairs. That means A atom will donate one lone pair, B atom will donate its lone pair. Okay. Then there can be compound where three atoms are there, A, B, C. A is donating one lone pair, B is donating one lone pair, and C is also donating one lone pair, like that. And based on that, the compounds have been classified. Suppose if there's a compound where there's only one atom which donates a lone pair. Now I'm not gonna repeat again that okay, there's a one compound where there's a one atom and that one atom is donating one lone pair. Now, if I'm saying it is donating one lone pair only, that means there's only one atom. Okay, because I have already mentioned you, let me clarify it once again. Okay, whatever different kind of compounds you take, if there is an atom which is donating a lone pair, it will always and can only donate a one lone pair. If there is a compound which is donating two lone pair, then there must be two atoms. Okay, if there is a compound which is donating three lone pair, then there must be three atoms. So based on that, how ligands are classified. See, based on that only, I'm going to write in the next slide so as to have not a messy thing on the same slide. Okay, so look here, denticity. So on this denticity only, how ligands are classified. Okay, first is monodentate. So basically dentate means what? Dentate means number of lone pairs donated. And I don't need to tell you what is meant by mono. Mono means one, right? So monodentate. So it is donating a single lone pair. Or it could be negative charge also. Negative charge can be treated as a lone pair. Okay. For example, all the halides. You can take all the halides here. For example, F minus, Cl minus, Br minus, I minus, ETC. I don't need to tell you ETC because there aren't any apart from this. Halides, then you have a hydroxide, OH minus, then you have a NH2, 1 minus, then you have a RNH, 1 minus, then you have a R2N, 1 minus. Okay, all of these are monodentate. They can donate a maximum one lone pair or a negative charge. Now in monodentate, I am showing you only anionic. These all are what? These all are anionic ligands. These are anionic ligands. Okay, now I am going to show you neutral ligands. Neutral ligands which are monodentate. For example, water. Now on oxygen you can see there are two lone pair, but oxygen at a time can donate only one lone pair. Similarly, you have ammonia which is having a single lone pair only. Then you can have amines. In amines you will see it is donating single lone pair. Secondary amine, you can have a tertiary amine, you can have a H2S donating a lone pair. Okay, and there are many. So all of these are what? All of these are monodentate ligand. Then you have a bidentate ligand. Now I'm gonna need more space than what I have anticipated, so I would erase the, oh sorry, what happened? Yes, yes, so I will have only bidentate ligand here. Bidentate. Now as per the name, bi means two, dentate means lone pairs donated. Two lone pairs are going to get donated here. Okay, how? Let's take the first example. Ethylene diamine. Ethylene, you can see here the di means two. There are two amine, right? So we're gonna write a structure CH2, CH2, NH2, NH2. So you can see here ethylene diamine. This is your ethylene, right? This is your ethylene. This is diamine. There are two amines. This can donate one lone pair. This can donate another lone pair. That is how two nitrogen can donate two lone pair. And that is how it is bidentate or didentate. Okay. Now, Let me take the another example here. The another example that we can take here is this oxalato. Now, how do you write oxalato? C double bond O, C double bond O, O minus, O minus. You can see here both the oxygen atoms can donate both the oxygen can donate one lone pair each, and there are two oxygen atoms, and that is how it is bidentate. Okay, through this it will be donating its lone pair. Let me take the metal also there now. Here your metal is there, N plus like that. Okay, similarly here also metal is here, okay. That is how the bidentate and monodentate ligands are all about. Now I'm gonna again leave you for a 15 or 20 seconds to have a look at it closely. Let me write it again. Oxalato. Oxalato. Okay. Chalo. We can move to the next type of a ligand now. Now I don't have much space here. So we have finished monodentate, bidentate. Okay. Now we can move to the next. That is Tridented Ligand. Tridented Ligand. Now tridentate, as per the name, tri means three, dentate means lone pairs donated, right? Your ligand is going to donate three lone pairs here. How? Let's see. Did I make a mistake here? Yes. Yes, now I'm going to have a lone pair here. Lone pair, lone pair, lone pair. And you can put your metal atom in the center here. M, N plus. Okay, I'm writing N plus. Not necessarily your metal has to be cationic. Sometimes it could be neutral also. Okay, but in this case, I'm putting a charge on it. Oh, yes. And what do we have here is this. What are this? These are coordinate bonds, right? As you must have studied them in your 11th. Okay, these are the coordinate bond which are being donated to your central metal atom. You can see here clearly as there are three lone pairs, right? This is the one, second, and third. 1, 2, and 3. And that is how it is tridentate. Then we're gonna have Tetradentate. This is Tridented. Tetradented Ligand. Now, as per the name, tetra, right? Tetra means 4. Tetra means 4. Again, dentate means lone pairs, right? It will be donating 4 lone pairs now. How? Let's see it again. Okay, by the way, what is the name of this compound? You can see here there are 2 ethylene, right? This is one ethylene. This is another ethylene. And how many amines are there? 1, 2, and 3, right? Then what do we call this compound as? Diethylene triamine. Because there are 3 amines now. 1, 2, and 3. Diethylene triamine, right? So that is how this is tridented ligand. Now let's see the tetradentate. Now in tetradentate you are going to have a 4 donating atoms, right? How? Let's see. Okay. Sometimes the structures might go wrong also. Okay. So don't mind it, because I don't like people to mark things up. I like you to produce things. You should be able to reproduce the structure as per your requirement. Okay. So we are going to need a 4 nitrogen there. How are we going to arrange it? Let's see. Okay, CH2, CH2, then you are having CH2, CH2. So the next type of ligand that we're going to see is Tri-Dented Ligand. So Tri-Dented Ligand, as the name suggests, right? Tri means 3. Dentate means how many? 3 lone pairs are going to get donated, right? Let's see what would be the structure of a 3 or tridented ligands. Okay, so as far as bidentate ligands are concerned, we saw the example of ethylene diamine, right, and oxalato. Now here also same type of ligands are going to be there. Okay, we are not gonna go much different than what we had seen for monodentate and bidentate. Okay, now let's see what it is. Tridentate. Now for tridentate, obviously we need to have 2 ethylene groups. Okay, so one ethylene group is this CH2, CH2, then another CH2 group here, CH2, CH2. Okay, so you have one nitrogen here, So this lone pair, and then you have another two nitrogen atoms, NH2, NH2. This lone pair, this lone pair, and all of these three nitrogen will be donating their lone pair to metal ion here, Mn plus. So just like that. That is how the tri-dented ligands are there. You can clearly see there are three ligands. This is one, this is second, and this one is your third, right? That is how three different nitrogen atoms will be donating their their lone pair of electrons to your metal atom. Okay, now the next dentate ligand is a tetradentate. Okay, now once I write that, I'm going to tell you the trick how to remember these different types of ligands. Okay, now this is tridentate. We are done with it. Next one is our tetradentate ligand. Now before I write this, let me tell you some simple trick for it. See, whenever I was talking about bidentate, okay, type of ligand, let me see here, ligand and ethylene groups, okay. So whatever type of ligand you take, just reduce one number and that many number of ethylene groups would always be there. Okay, so when we had a bidentate ligand, we had a single ethylene group. Remember, ethylene diamine. Similarly, when you have a tridentate ligand, tri means what? Tri means 3. So 3 minus 1, 2. So you have a 2 ethylene groups we just saw here, right? Similarly, when you have a tetradentate ligand means 4. 4 minus 1, 3, right? So for tetradentate ligand, we are going to have 3 ethylene groups, right? And after that, you need to arrange the nitrogen atoms there. Okay, now let's see how I'm going to arrange those. See, ethylene group here, CH2, CH2. This is your first ethylene group. Then you have another CH2. As I told you, it's a tetradentate, right? So 4 minus 1, 3. That means we are going to have 3 ethylene groups there, right? So now you will have a nitrogen here. Similarly, the another nitrogen would be here. And then you will have other 2 nitrogen atoms here. See, lone pair, lone pair, lone pair, lone pair, and all of this lone pair would be donated to your central metal ion from all the 4 sides. That is how tetradentate ligands are going to be. And I hope it must be pretty much sorted for you now. Why? I just told you the trick here, right? See, the trick is very, very easy. Just remember this trick. Ligand and ethylene groups. Whatever type of ligand you want to have, just reduce one number and those many number of ethylene groups you are going to have. Okay? Because sometime no. See, first I took ethylene, then I put a nitrogen in it. Then I took another 2 ethylene groups, then I put a nitrogen into it. Then I take 3 ethylene groups and then I put a nitrogen around it. So sometimes this process becomes a little bit complicated. Okay, so just as to reduce that confusion in your head, I made this trick. Okay, so just remember this trick. I'm going to leave you again with just 15 seconds. Just take a look at it. Okay, I hope this must have been clear to you now. Now let's see some other type of ligand which are pentadentate and hexadentate. Okay, so the next one is your, oh, let me change the color. Pentadentate. Again, penta means what? Penta means 5, dentate means lone pairs, right? Now here, this ligand is going to donate 5 lone pairs. Okay. Now, as far as remembering the structure or type of ligand here, you don't need to follow the procedure which we had followed for bi, tri and tetradentate, okay, ligands. Now it is different. Here you are going to have only single ethylene. Okay, let's see how we are going to plan the structure. So first you are going to have ethylene here, CH2, CH2, ethylene. First you are going to have ethylene, okay. Then you are going to have ethylene diamine. That means you will have one nitrogen here. Okay, just a sec. Yeah, ethylene diamine, nitrogen, nitrogen. Ethylene diamine tri acetate. What is mean by acetate? CH3 dash C double bond O minus. That group is called as acetate group. Okay, see here. CH2 C double bond O minus. So that is another. Then you will have another acetate group here. Lone pair. Similarly, you will have another acetate group here also. So CH2 C double bond O minus. So how many donating sites do we have? Let's check it out. See, this one is your first, this is your second, this is your third, this is fourth, and this is fifth. So that is how 5 donating sites are there, and through these 5 donating sites, this ligand is going to donate its lone pair of electron, and that is how you call it as pentadentate ligand. Okay, now take a look at its structure once again. Now the next structure that I'm going to tell, it's similarly like this, same structure. Okay, no difference. See, ethylene diamine. So whenever I say diamine, that means 2 dentate have already been there. Diamine tri acetate. Each acetate is donating 1 lone pair. Tri means 3. So 3 acetate will be donating 3 lone pairs. So 3 acetate, 2 nitrogen. Together 3 plus 2, 5. So 5 lone pairs are being donated in that fashion. The next structure is hexadentate. Hexa means 6, right? 6er. Hexadentate. 6 lone pairs will be donated, and structure is same. Again, we want to start with ethylene diamine, ethylene diamine, but this time not triacetate, this time tetraacetate. Ethylene diamine tetraacetate, just like that. Take a look at this structure for 15 seconds. Okay, chalo, I hope this must have been clear to you. Now let's see the next, which is the last one, hexadentate. Oh, let me change the color once again. We have the red color only. Hexadentate ligand. Again, hexa means 6, dentate means lone pair. You know that. I don't need to tell you that again and again, right? It is quite easy for you to get it now. So as I told you, how the structure is ethylene. So first draw the ethylene, right? First drop the ethylene, then put a 2 nitrogen on both sides because it's ethylene diamine, right? So ethylene nitrogen, right? Ethylene diamine tetraacetate. So in the previous structure we had a 3 acetate group. Here we are going to have 4 acetate group. CH2, C double bond O, O minus, O minus, C double bond O, O minus, O minus. Okay. Now, how are we going to have all the donating sites? Let's take a look at here. This is first one. I mean, there is no number, there is no chronology here. I'm just telling you how 6 donating sites are there. Okay. Yeah. One more thing was left, that is to put the lone pair right in front of nitrogen. So this is your third one, this is your fourth one, this is your fifth one, and this is your sixth one. That is how you have 6 donating sites, which is called as hexadentate. Okay, now let me tell you the structure of this compound. This compound is very famous. This compound is also used as a, what should I say? This is used as a medical, it is used as a medical agent to remove or to abstract the mercury from your blood. Whenever the mercury poisoning is there, the injection of this compound is given, and this compound is then chelates the mercury out of your body. Okay, this compound name is EDTA. It's very famous compound, EDTA. What is the full form of this? The full form of this compound is ethylene, which is right in front of you, right? Ethylene, then you have got a 2 amine group, ethylene diamine tetra acetate, ethylene diamine tetra acetate. That is how the EDTA structure is this. Okay, now I'm again going to leave you for a 15 seconds to take a look at this structure very clearly. Okay. Okay, chalo. Now let's move to the next part of our session. So I hope all the type of ligand must have been pretty much clear to you now. So the next is type of complexes. Now complexes means you have already come to know now, right? Metal coordinating with some ligand, okay, maybe by primary valency, secondary valency, and all of that. For example, K3 EpCN6, K4 EpCN6, these are called as complexes. Okay, now there are 2 types of complexes here. Okay, let's see each one of them. One is homoleptic complexes, homoleptic. Another is heteroleptic, okay. Now what is mean by this homo? Homo means same, okay. So leptic does not have as such meaning here, but same ligand. I would rather say same ligand. So only one type of ligand, or you can say only one type of ligand. Okay. Another is hetero. Hetero means we already know, right? Hetero means different. So we can rather say two or more type of ligands are coordinated or ligated to your metal atom or ion. Two or more type of ligands. Okay, two or more type of ligands. Let me give you some simple examples. We can take a simple example. For example, okay, let's take a chromium wala example. Yeah. So CrH2O 6Cl3. Now what is your ligand here? This might confuse you a bit. So ligand is this only. This is your ligand. And what is your chloride ion doing there? This is your counter ion. This is your counter ion. Okay. Now your counter ion can act as ligand. There is no doubt about it. Okay. But as far as this particular example is concerned, counter ion here is outside the coordination sphere. This is the coordination sphere, as we know that. CrH2O is enclosed in some bracket. That bracket is called as your coordination sphere, and chloride ion is just outside it. Okay, so chloride ion is not acting as a ligand here. Okay, but in the very next example, it can act as a ligand. I'm going to show you that. Let's see now. Okay, now look at this example. Cr. Now I'm going to have only 5 water ligand there. I'm going to bring one chlorine ion inside. I'm going to put one water molecule outside, and out of 3, 1 chlorine atom has come here. So 2 chlorine atoms are outside. Now here you can see there are 2 types of ligand here. This is one, another is this. So now this is not homoleptic, this is heteroleptic. Basically, if you have two or more different type of ligands inside this coordination sphere, it would be classified as heteroleptic complex. And suppose if you have only one ligand inside the coordination sphere, it would be homoleptic complexes. I hope this must have been pretty much easy and clear to you, but still I'm again going to leave you for 15 seconds, so take a look at it closely. Okay, I hope this must have been clear to you. Now let's move to the next segment. Now next segment is very most important part here is Iupac nomenclature, right? You must have seen Iupac nomenclature in the organic chemistry, right? In organic chemistry we had seen it. What is the long form of Iupac? IUPAC, International Union of Pure and Applied Chemistry. Okay, what does they do? They set the different kind of rules for naming the compound, and so as to make it easier for us. Okay, because there are huge pile of compounds. You all know that the huge number of compounds are there, right? So it will be difficult for us to remember all of those compounds name. So there has to be some systematic rules. Okay, that is why these rules are there. Okay, now let's read it out, all those rules, and we're gonna see their application too. Okay, now what is the first rule? The cation. The cation is named first in both positively and negatively charged coordination entities. What is mean by positively charged or negatively charged coordination entities? Okay, now let me give you a quick example here. Now, for example, suppose you have a compound called K3FeCN6. Now again, FeCN6 is what? This is your coordination sphere. This is your coordination sphere. Okay, K3. As we had seen in homoleptic and heteroleptic examples, what was chloride ion doing there? Chloride ion was acting as a counter ion. Similarly, here K3 is acting as a counter ion. So K3 is what? Potassium. What is the charge on potassium? Plus 1, right? So 3 potassium would have 3 plus 1 charge. So plus 3 basically. So if you brush aside the potassium, what we gonna have is FeCN6 3 minus, right? So FeCN6 3 minus, so that is the charge on this sphere, right? So basically it becomes 3K plus FeCN6 3 minus, right? So that coordination sphere is what? It's a negatively charged coordination entity. That is what they meant here. Oh, I can give you another example here. Is this CrH2O Cl3. Now here couple of minutes ago we saw this example, right, where chloride ion was acting as a counter ion. Now if you try to dissociate this, what would you have? You would have CrH2O 6 3 plus 3 Cl minus. Now look at this. This is cation now, right? Now here coordination species is cation. Here counter ion was cation. So what do they mean by this first rule is that whenever we are naming this compound, it is the cation which has to name first. Okay. So if you are talking about this example, it is called as potassium, because potassium is there. Now potassium hexacyanoferrate. Now why am I saying ferrate? That you will see in the other rules. Okay. But for now, the name would be potassium hexacyanoferrate. Here again, here coordination sphere itself is cation. So you need to name it first. How? Hexaquochromium, into bracket its oxidation state, hexaquochromium 3 chloride. Okay, that is how you name the compounds. Okay, well, we're going to see illustration as this rule finishes. Okay, but with each rule I'm giving you some information. Okay, now what is the next rule says? The next rule is the ligands are named. The ligands are named in alphabetical order before the name of central atom or ion. Now here, before I put a central atom's name, whatever ligands are there, I mean, it is not necessary that you will always have only one type of ligand, the one we had seen in homoleptic, right? In heteroleptic, we had seen there could be different type of ligands, more than 2. Okay, so whenever you have a more than 2 type of ligands, you need to name them in a alphabetical order, just the way we had seen in organic chemistry. Okay, chalo. So that we will see. Next is names of the anionic ligands end in O. For example, F minus, Cl minus, Br minus, O minus, sorry, I minus. So fluoride, otherwise, see, as a matter of fact, we call it as a fluoride, but whenever it will come in coordination entity, it is called as fluorido. Chloride will be called as fluorido, bromine will be called as bromido, iodine will be called as iodido, and so on. So, and that is how the anionic ligands will end their names in. And those of neutral and cationic ligands are the same except the aqua for water. See, for neutral and cationic ligands, you would name them as their original name. Okay. However, there are some cases where you don't call them as such. For example, for water, you call it as aqua. For NH3, you call it as amine. Okay. CO for carbonyl, nitrosyl for NO. Okay. And lastly, while writing the formula of coordination entity, these are the name in brackets. So that I don't need to tell you, that you already know. Obviously, we need to write them in brackets. Okay. So that is how all these rules are. I hope they must have been pretty much clear to you. Okay, let's move now. Now, the next is prefixes. Prefixes mono, di, tri are used to indicate the number of individual ligands in the coordination entity. That is obvious. Whatever number of ligands you have, to indicate their number, you need to use the prefixes like mono, di, tri, tetra, penta, hexa, hepta, deca, like that. Okay, we know that. We had seen that in organic chemistry. And when the names of the ligands are include numerical prefixes, see, there are some ligands which already has a prefix in them. For example, the ligands which are multidented. Multidented, by that, by that I mean the bidentate ligands and thereafter. For example, ethylene diamine. Ethylene diamine is a bidentate ligand, right? Now there could be two ethylene diamine in a single compound. So whenever there are already two ethylene diamine, you can call it as a diethylene diamine, right? That would sound quite awkward. So instead of bi, you would say bis. Bis means two, and then you will put into bracket ethylene diamine. So that bis will serve the purpose of calling it as bi. Okay. So, but that is not for all the type of ligand. It is only applicable to those ligands which already have a bi, tri, tetra, these prefixes in their name. Okay. So as I'm telling you, then the terms that you need to use here is bis for 2, tris for 3, tetrakis for 4. Okay. For example, NiCl2, PHP32. So this is named as dichlorido. As I told you, chloride is a negatively charged ligand, so you will call this as a dichlorido. Okay, but as I told you, now this PPH32 phosphine, you can't call it as a di. So you need to put bis there because there are two, right? So bis into bracket triphenyl phosphine. Okay, because there is already tri they have used in their name. Triphenyl phosphine is the name of ligand. So to avoid that confusion, we have put the bis. So bis triphenyl phosphine nickel 2. Okay, that is how the names are being given. Then nextly, if the complex ion is cation, the metal is named same as the element. Okay, complex ion means what? Coordination species. I would rather say coordination sphere. If that is cationic, the name of the metal is named as such. For example, for chromium it's a chromium, for iron it's a iron. However, if the coordination sphere is an anion, for example, we had seen K3FeCN6. In K3FeCN6, whenever you brush aside the potassium, you get FeCN6 3-. So that coordination sphere is what? It's an anionic. So that time you can't call iron as iron. As I told you while giving that example also in the very first rule of Iupac. That I will tell you about it later on, and that's the time has come now. So FeCN6 3-, the name of the coordination sphere would be named as ferrate. Okay. Now there are different names for different metal atoms whenever they are in a coordination sphere which is negatively charged. So if it's a cation, it will be named as straightforward cobalt or platinum, like that. Okay. But if the complex ion is an anion, the name of the metal should end with suffix ate. For example, cobalt would be named as cobaltate. So I'm going to tell you all those names. Cobalt would named as cobaltate. So cobalt we already know. I'm going to add this suffix. What suffix? Ate. Okay. Iron, your iron Fe would end as ferrate, like that. Gold Au would named as aurate. Ag, silver, would be named as argentate. Okay. Cu, copper, would be named as cuprate. Zinc would name as zincate. Okay, like that. You can take different example. Vanadium will end as vanadate. Chromium would end as chromate. then what? Manganese would end up as manganate, and so on. That is how you name all those compounds. Okay, it is very, very simple like that. Okay, so I hope this must have been clear to you, but still again I will leave you just for 15 seconds to have a look at it. Okay, shallow. Let's move to the next part now. Yes, now we're gonna see how to name this compound. As I told you that we're gonna see the example of it. Okay, let's say it now. Okay, I'll use this color. Now, see, the chromium atom is there. Okay, now this coordination sphere, the coordination sphere that we have is having a positive charge. Why? Because the counter ion is anionic. Chloride ion is there, right? So when you remove 3 chloride ions, what would you have? 3 plus charge there, right? So 3 plus charge is there. That means what? That means it is going to have no ATE after the name of the metal as a suffix. Okay, but there are 2 types of ligand here. One is amine, another is water. Water is called as what? What is called as aqua. So I'm going to write it here. Amine, aquo or aqua. Now between them, which will come first? That we need to find out. Now see how to find that out. In both of them you have A as the first. So A will not decide which will come first in alphabetical order. However, we know that M comes before the Q, right? M comes before the Q. So therefore amine would come before. And then how are we going to name it? It is, how would you name it then? Triamine. Triamine, tri-aqua or aquo, whatever it is. Triamine, tri-aqua, chromium. Chromium 3, because that is the oxidation state of your chromium here, right? Triamine, tri-aqua, chromium 3, chloride. Now you might ask me, sir, why didn't you tell that 3 chloride ions are there? Because I don't need to. Why? Because that is self-explanatory. Whenever I say chromium 3, that means oxidation state of chromium is +3, and to counterbalance that, we will need 3 chloride ions. Okay. Or let me tell you one simple thing. Whatever ions, whatever counter ions we have outside the coordination sphere, be it a cation or be it anion, we will never tell their number. We just put their names. Okay, because whenever I put, or you need to put the oxidation state of metal ion always. So putting the oxidation state of metal ion there will explain it that how many complements, sorry, how many not complementary, how many balancing cation or anion or counter ions are there. Okay, so that is how the name of this compound is. Now here potassium is there, right? So when the potassium is there, that means the charge on this complex ion is what? It's an anion. Okay, charge on complex ion is anion. So what would you do now? Obviously you need to put ferrate there. Okay, but before that we're gonna put this name. So there are 4 cyanide ion there. There are 4 cyanide ion there and 4 potassium there. I guess there's a little bit confusion here because there can't be 4 cyanide here because there has to be 6. There has to be 6 cyanide ion there. Okay, so how are we going to name it? 6 cyanide. So how you going to write hexa? But as I told you, cation is named first. Okay, so sorry, my bad. We're going to write the potassium first. So potassium is there. Potassium. Then how many cyanide atoms? Sorry, how many cyanide ligands are there? 6, right? So potassium hexacyano, potassium hexacyano ferrate. What is the charge on metal ion? This will produce -6, this will produce +4. So charge together becomes -2. Therefore, metal will have a charge +2. So potassium hexacyano ferrate 2. That is it. That is how you name this kind of compounds. It is that easy. Okay. When you practice it more and more by keeping all those rules in the back of your head, you will understand how to write their names. Okay, I hope this is pretty much useful for you. Again, I'm going to leave you just for 15 seconds to take a look at it closely. Okay, chalo. I hope this must have been clear. Now let's move ahead. Now the isomerism. Now we already know what isomerism is, right? Isomerism is a phenomenon where two compounds are having same molecular formula but have a different structural formula, because structural formula is different, and structural formula is the one which decides how the compound is going to behave in a different physical or chemical experiments. Okay, so you already know what isomerism is. I'm not gonna explain much about it. Okay, only thing is that I'm gonna tell you how different types of isomerism can be displayed by your coordination compound. Okay, the very first is stereoisomerism. We already know what stereoisomerism is, right? Stereoisomerism, stereo means what? 3-dimensional. So the isomerism which arises due to 3-dimensional difference. I mean, isomerism which arises due to difference in the structure of the compound in a 3-dimensional space. Okay, sometimes compound might look the same, okay, in a 2-dimensional thing, but in a 3-dimensional space they might look different. Therefore, in a 3-dimensional space, if there is a difference, then that can cause compound to have a stereoisomerism. Okay, so stereoisomerism, again there are two types. One is your geometrical, another is optical. We know geometrical isomerism, right? Basically, it also called as cis-trans isomerism. That is called as geometrical isomerism. Then we have optical isomerism. Optical isomerism is what? The isomerism which is involved in rotating the plane of a plane polarized light is called as optical isomerism. For example, dextro-rotatory, levo-rotatory, all of those kind of isomerism come into optical isomerism. Then this isomerism we had seen in organic chemistry also. This isomerism we had seen in organic chemistry too. Okay, but this isomerism, linkage, ionization, coordination and solvent, this we haven't seen. That we're going to see as far as this coordination chemistry chapter is concerned. For example, linkage, ionization, coordination and solve it. Okay, now let's see each one of them one by one. Okay, I'm going to tell you what this kind of isomerism, linkage, ionization, coordination, solve it there only. Okay, but for the, as I'm going with the order, so first we will see what is geometrical isomerism. Okay, now geometrical isomerism. See, geometrical isomerism obviously it arises due to symmetrical distribution of ligand across the coordination sphere around the metal atom. Okay, so there are two types. One is square planar compound also show geometrical isomerism. Then you have a octahedral complexes. Okay, that is your octahedral, and this is your square planar. Here metal is at the center here, here metal is here. Okay, structure we're gonna see obviously. Okay, but let's see each one of them one by one. So square planar, MX2L2, MA2XL, MABXL. What is this? X2, X is a type of ligand and L is also type of a ligand obviously. So there are two same ligands are there. X, there are two X, there are two L. Here there's a only one ligand only, and their other two ligands are different. Here all the four ligands around the central metal atom are completely different. Okay, so let's see the square planar complexes which shows geometrical isomerism. The first we're gonna see is MX2L2. So MX2L2. Okay, the very famous example of this type of complex is cisplatin and transplatin. Okay, let me show you. Platinum, NH3, chloride, straightforward, and you can easily guess which compound is which. This is cis. You can see both the both the amine groups are on the same side. Similarly, both the chloride ions are on the same side. So this is your cisplatin. This is your cisplatin. Then what must be your transplatin? Not that difficult to guess, right? Platinum, NH3, sorry, oh, what happened? Sorry, yeah. So let's leave that chlorine like that only. It's not going to matter much. Another chlorine here. So what is this? This is transplatin. Cisplatin, transplatin, right? And let me tell you for your information, this cisplatin is also a anti-cancer agent. It is anti-cancer agent. Okay, cisplatin, transplatin. Now, what was the another type I was talking about? Another type was, let me put the demarcation there. So another was what was that? AA2XL. Yes, it was that one. Let me check it. Yes, MA2XL. So MA2XL is, let me take an example. Again, you can take the example of platinum or palladium also. So Ma2XL. Now here, see, ethylene diamine, nitrogen. This is ethylene diamine, and Oh, sorry, maybe I made a mistake here. MAA2XL. So platinum AA2, that means it's a bi-dented ligand, and X and L, these are two different types of ligands. Okay, so A2, that means we can put this as different AA2. Now let's see the another type of a square planar complexes which shows geometrical isomerism. For example, MAA, and what was that? XL, right? MAA XL. Now AA is what? There are two same ligands, and XL are different ligand, obviously. So the example for this is this: platinum, chlorine, bromine. Oh, again I put this wrong way. Wait. Yes. Platinum, pyridine, chlorine, bromine. Okay, this one. And then the another one is PY, chlorine, and bromine. So I don't need to tell you what is what. This is what? This is your cis. And this one is what? This one is your trans, right? Cis and trans. That is how this square planar complexes shows a different kind of geometrical isomerism. Now we want to see the next part is that these are the two complexes. Sorry, these are the two type of complexes which shows geometrical isomerism. Now let's see the third type, where all the four ligands are completely different, right? So the next part is this: M, A, B, C, D, right? Now let me take the quick example of this. Is this platinum, then you have a chlorine, bromine, iodine, and nitro group. Now how are we going to find? See, these are not basically cis and trans type of isomerism. Okay, they are different, but we can find that different type of geometrical isomerism they do show, but not exactly like a cis and trans. Okay, I'm going to show you how this compound will show different types of isomers. How? See, what you need to do is that you need to keep the chlorine constant there. You need to keep one of the ligand constant, because then the relative positions might change and that might confuse you. So I'm going to keep chlorine there itself, and I'm going to change the other ligands around it. Let's see. This is the first one. Okay, in second one we are going to rotate this ligands in a clockwise manner. That means bromine will go to iodine's place, iodine will go to the nitro place, and nitro will come to the bromine's place. See, platinum. Now you will have a chlorine still there, nitro would be here now, bromide or bromine would be here, and then what? Iodine would be here. Now see, do these two complexes look different? Yes, they look completely different. Okay, now the third one, again I am going to move this in a clockwise fashion, keeping the chloride constant there. So iodine would come to the nitro's place now, Nitro would go to the bromine's place and bromine will go to the iodine's place. Oh, sorry, I made a mistake here. Yes, so bromine would go here, and that is how you got a 3 type of ligands. Now if you try to rotate, it again clockwise fashion, bromine would come here, iodine would go here, nitro would go here, and that will give you the very first compound. That means the possibilities of rotating these ligands around the chloride and metal ion are finished. So these are the only 3 possibilities by which you can show the geometrical isomerism by this particular compound. Okay. So I'm going to leave you again for 15 seconds. Take a look at it. Okay, sure. Let's move to the next slide now. Yes, so this is done with the square planar complexes. Now we're going to see it for the octahedral complexes. Okay, now let's go back a bit. Yeah, so this was your octahedral complexes MX2L4. That means the 4 ligands are same and other 2 ligands are different, and here 3 ligands are same and other 3 ligands are different. So these are the 2 types. Okay, now let's see each one of them in an octahedral way. Geometrical isomerism by octahedral complexes. Okay, first we're going to see is this MX2L4. Okay, now you can take an example of cobalt. Okay, NH3, 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 NH3. This is not a bond, okay? This is just to show the geometry. Okay, then you have a then you have a chloride here. So now, it is not so difficult to guess that this is what? This is your trans. Now, you might say, sir, amine ligands are on the same side, but also on the opposite side, right? So, these 2 amines are on the same side. These 2 amines are on the opposite side of these 2 amine ligands. So, amine is not going to decide whether this compound is cis or trans. The deciding factor is chloride. Look at this, chloride ligands are exactly opposite to each other. So that's why it is trans. Okay, then what is cis? Let's see. So cobalt, chloride. NH3 and yes, one more chloride here and ammonia, sorry, yeah, amine. This is also not so difficult to guess, right? You can see 2 chloride ligands are on the same side and 4 amine ligands are on the same side. So that was trans. What is this? This is cis, right? That is how octahedral complexes of MX2L4 type shows isomerism. Okay, take a look at it once again. Okay, so chalo, I hope it must have been clear to you. Now let's see the last geometrical isomerism. Oh, so there is no space here, but I am going to write it in that corner and one in this corner. Okay, it was of what type? MX3L3, right? So there are 2 type of ligands that it shows. Sorry, there are 2 type of complexes that it shows. So the example I'm going to take is this: CrNH3, NH3. You have a chloride here, chloride here, then another chloride here and another NH3. Okay, so you can see here all the amine ligands are on the same side. You can see there all the amine ligands are on the same side, all the chloride ligands are on the same side. So you can call this as cis, you can call this as cis, no problem, or it is also called as facial. Okay, in shortcut it is written as FAC CrNH3 PCl. Sorry. Okay, so that is cis or facial. And another type that we're going to see now, since we have a less space, we're going to see it on this side. Now we're going to replace one chlorine from here to there. Chloride, NH3 would stay there only. This chloride would remain here. This chloride would remain here. Okay, one NH3 NH3, yes, this NH3 is completely, let me have a demarcation line here so that it would not confuse you. Okay, okay, this is of MX2L4. Now this is of MX3L3 and NH3. Okay, so this type is called as meridional, or it is also called as mer isomer. Meridional, or you can call this as trans. As you can see, amine ligands, two amine ligands are present opposite to each other. Okay, so that is also called as meridional isomer or trans isomer. Okay, so I hope all of this geometrical isomerism game has been quite easy for you to understand. Now we're going to move to the next part, that is optical isomerism. So the next thing that we are going to see is optical isomerism. So what is optical isomerism? As we all know that whenever a plane polarized light is passed through a compound which is not symmetrical, whenever a plane polarized light is passed through a compound which is not symmetrical, it will rotate the plane of a plane polarized light either to the right hand side or to the left hand side. If it rotates it to the right hand side, it is called as dextro-rotatory, and if it rotates it to the left hand side, it is called as levo-rotatory, right? We had seen all these concepts in organic chemistry pretty well. Okay, so I'm not going to take you back there that how this light is produced and how compound rotates. We're just going to see what are those coordination compounds which displays such optical isomerism. Okay, but before moving to that, let's see the different coordination number. For example, there are two coordination number dominantly we have for coordination compound. One is coordination number 4, another is coordination number 6. So in coordination number 4, we have two compound. One is tetrahedral, which I would just write TD, and another is square planar, right? So as far as tetrahedral compounds are concerned, tetrahedral compounds do show optical isomerism. That means they do rotate the plane of a plane polarized light to the right or to the left as well. But the thing is that they are not resolvable. Why? Because say in organic chemistry, the groups around the carbon are not that much labile. But as far as coordination compounds are concerned, the ligands around a metal atom or ion are extremely labile. That means they are moving around a metal, they are exchanging their position so fast that it becomes almost difficult for us to find out which is dextro, which is leo. And that is why the tetrahedral compounds, I would rather say, they are non-resolvable. They are completely non-resolvable. You cannot resolve them. Okay. As far as square planar compounds are concerned, square planar compound has what? They have plane of symmetry. Remember, having any element of symmetry, there are different elements of symmetry, plane of symmetry, then you can have a bisymmetry, then you can have an inversion point. Okay, all of these are symmetry element. So having any of the having any of the symmetry element will stop or will restrict compound to have optical isomerism. Remember that. And your square planar compounds, your square planar compounds, they are having what? They are having plane of symmetry. So since they are having plane of symmetry, that makes them what? That makes them optically inactive. That makes them optically inactive. Okay, now you need to understand one point here. There are some, well, though even after this, there are some compounds of square planar which shows some kind of optical isomerism. Okay, but that is beyond the scope of your NCERT book. Okay, it is for the advanced exam, so that is why I am not telling you here. Okay, now this is for coordination number 4. Now let's see some of the compounds of coordination number 6. See, in coordination number 6, let me tell you one point very clear here. Okay, as far as coordination compounds are concerned, you need to understand that only those coordination compounds can show optical isomerism which has at least, remember or mark my words carefully again, only those coordination compounds does show optical activity which are having at least one ligating ligand. What is mean by ligating? Sorry, chelating ligand. What is mean by chelating ligand? We had seen the ligand, right? Bidentate, tridentate, tetradentate, and so on. So all those ligands beyond the denticity, beyond the which are having denticity 2 or more than that, are called as chelating ligands. So only monodentate ligands are not chelating ligands. Apart from that, all the ligands are chelating ligands. Okay, so those ligands, they should be present to show optical isomerism. So I'm going to tell you one example here. Let me show you that. Cobalt, ethylene diamine. This compound, and well, you can take the mirror image of this compound. So whenever you take the mirror image of this compound, what do you get is this. This compound is D. D means what? Dextroprotatory. And what is this? L. Levoprotatory. Okay. As far as these compounds are concerned, it is pretty much easy to find out which is dextro, which is levo. You can see this loop is on the right hand side. Right hand side means what? Dextro. Simple. This loop is on the left hand side. Left hand side means what? Levo. Okay, that is how this coordination compound shows optical isomerism. Now I'm going to leave you again for 15 seconds. Just take a look at it. Okay, so I hope this must have been pretty much clear to you. Now let's move to the next isomerism, and that is ionization isomerism. So as the name suggests, ionization isomers, right? So what is mean by ionization isomers? The compound which are able to give different ions upon dissociation are called as ionization isomerism. Now you need to understand here, we had seen the coordination entity. Remember, we had a coordination sphere, and just outside that we have a counter ion. Okay. Now this counter ion generally does what? This counter ion balances the charge of your metal atom or ion. I wouldn't say atom, ion only. Okay. Now, for any compound to show or display ionization isomerism, it should be, I mean, any compound to show ionization isomerism, there is a necessary condition that counter ion should be able to act as a ligand. If the counter ion is able to act as a ligand, then and then only that compound shows ionization isomerism. Let me give you a quick example of it. Okay. So look at this example now. Let me change the color. Now you can see here the molecular formula of this compound is exactly same. Okay, but the ions that it would give upon dissociation are completely different. And how do we find that out? Let's see. Suppose if we are reacting this compound with two compounds, if we are reacting this coordination species or a coordination compound with two compounds, one is your AgNO3. Let me change the color of that also, so that it will be easy for you to identify. AgNO3, and another that we're going to react with barium chloride. Now AgNO3, now this bromine here is inside the coordination sphere. It is not outside the coordination sphere, because of which AgNO3 with AgNO3 it would not react, but it would form a PPT with BaCl2. What PPT? PPT of barium sulfate. PPT of barium sulfate, which is what? Which is white in color. Okay. Similarly, this compound, if you take this compound, it would react with AgNO3. It would form a PPT. But with BaCl2, it would not react, because barium chloride is able to react only with sulfate. So it is quite easy for you to identify. Here, this compound gives you this coordination sphere plus SO4 2- upon dissociation, and that sulfate is identifiable by treating it with the barium chloride, because that gave us barium sulfate white precipitate. Similarly, this compound upon dissociation gives you this complex ion plus Br-, okay, which gave us the white PPT. Is not white PPT, PPT with AgNO3, but it does not react with barium chloride. That is how ionization isomerism exists. So if I summarize it, it is that isomerism where two compounds are having same molecular formula, but they give different ions upon dissociation. Okay, and that is not just one example here. There are so many. I can give you the example of a compound which I took as an example to explain Werner's coordination theory also. Remember, in that example, there were four compounds. One compound gave you one chloride ion upon dissociation, another gave you two, third one gave you three, and fourth one gave you none. Okay, that we were able to find out by treating them with the AgNO3. Okay, that is how the ionization isomerism exists. Okay, now I'm going to leave you again for 15 seconds to take a look at it. Okay, chalo, moving to the next point now. Linkage isomerism. Now, linkage isomerism, where do we, as the name suggests, linkage, right? So it is all connection with the link. What link? How the different ligands are linked to the central metal atom or ion in coordination compound. Linkage isomerism is shown by only those compounds, so or only those complexes which are having ambidentate ligands in them. Okay, so what is mean by these ambidentate ligands? See, ambidentate ligands. So ambidentate ligands are the monodentate ligands only. Ambidentate ligands are monodentate ligands only, but they can or they are able to ligate through different site at a different point. For example, let me give you an example. Okay, look at this example. Nitro N double bond O minus. So here this nitro group, basically it is nothing but what? Nitro group. This nitro group can coordinate through metal atom, or it can coordinate through nitrogen also. It can coordinate through nitrogen also. It can coordinate through O. So this is called as nitrito, this is called as O nitrito. Okay, it is that simple. So nitro group, similarly your cyanide group. Cyanide can coordinate through your carbon, or it can coordinate through your nitrogen also. So this is cyano, this is isocyano. So let me make this very simple, not complicated. Any compound, so any coordination compound which is having ambidentate ligand in them can show or does show linkage isomerism. It's very simple. Or let me put an example here. Cr NO2 3 H2O 3 Cl3. Okay, now here you can, oh sorry, my bad, just a sec. No, there is nothing wrong with it. Now this compound, another compound I am going to show you, ONO 3 H2O 3. Now both these compounds are linkage isomers of each other. So basically all those compounds which are having nitro, cyano or thiocyano, SCN or NCS. Okay, so all those compounds which are having this as a ligand in them can show linkage isomerism. It is that simple and straightforward. Okay, again take a look at it. Okay, so moving to the next point, that is coordination isomerism. Now coordination isomerism is basically what? You can call this as an exchange of ligands between two coordination compound. Okay, it is nothing but that only. It is nothing but the exchange of ligands between the two coordination complexes. okay, where one coordination compound acts as a cation, another coordination compound acts as an anion. Let me give you an example very quickly. So cobalt CN6. Now the oxidation state of cobalt here is 3, okay. Another compound is CrNH36, okay. Now let me tell you very quickly that this compound is having, the coordination number, sorry, not coordination, oxidation state of cobalt is +3 and chromium is also +3, okay. But why these compounds are together? It's because each cyanide has -1 charge. So 6 cyanide will have -6 charge and +3. That means this compound, this coordination entity has 3- charge here, okay, and this coordination entity has +3 charge because amine ligands are completely neutral. So whatever charge chromium possesses, same charge would be here. So 3- plus 3-, that is how they're existing as a cation and anion. Now here, now there is a catch here. There is an exchange of, I won't say catch, but that now there comes a phenomenon where there's an exchange of ligands here. How? See, now your cobalt would see bonding with ammonia, 6 ammonia, okay. Now it will have a 3+ charge, and now your chromium would see bonding with cyanide, 6 cyanide, so 3+, 3-, like that. So that is how coordination isomerism exists, okay. Again, take a look at it for a while. Okay, chalo, moving ahead. Now the last one is solvent isomerism. Now let me tell you, there is no much difference between ionization isomerism and solvent isomerism. You can say solvent isomerism is an special case. Solvent isomerism is a special case of an ionization isomerism, okay, where the ligands are especially water molecule. For example, take a look at this. Cobalt H2O 6 Cl3. This, then you are having CrH2O 5, 1 chlorine inside, 2 chlorine outside, 1 water molecule outside. Similarly, you can have COH2O 4 Cl2 Cl H2O2, and you can also have CO H2O 3 Cl3 H2O3. Now take a look at this. Cl3, Cl, 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 like that. Now here you can easily find out. Now how do we know that different water molecules are there? See, whenever you are reacting this with concentrated H2SO4. So whenever you're reacting this with a concentrated H2SO4, what happens is that there is no dehydration. Here there is no dehydration. Why there is no dehydration? Because water molecules are not outside the coordination sphere. Water molecules are not outside the coordination sphere, they are inside the coordination sphere, so they are protected. Here there is a 1 water molecule outside the coordination sphere, here there are 2, here there are 3. So because of which there is an dehydration here. there is an dehydration of water molecules. Here dehydration of one molecule, here dehydration of two, here dehydration of three water molecules, and that is how. Now here water can also act as a solvent, right? Water is a solvent only, and that is why this type of isomerism is called as solvent isomerism. Okay, take a look at it again. Okay, chalo, moving ahead now. Now bonding theories. Now we're gonna see. Now we had seen isomerism, how different compounds show different kind of isomerism, their Iupac nomenclature, and everything regarding their structure. Now we're gonna see how these compounds are actually forming a bond, because that is how you will understand much about them in a depth. Okay, so let's see the bonding theories. So bonding theories, one of them is VBT, another is CFT, another is MOT. Okay, now MOT is actually outside the scope of this book. Okay, but I'm just telling you that it is there. VBT means what? VBT means valence bond theory. CFT means crystal field theory, and lastly MOT is molecular orbital theory. Okay, so all of these theories are there. MOT is not for you to study. You can study it at the advanced layer. That means if you are doing bachelor in science or master in science in chemistry, then you would study it. But now it is not that for you. So we are only going to see VBT and CFT. Okay, so let's see each one of them. Firstly, VBT. Okay, now before I tell you what is VBT, see, let me tell you some of the postulates of VBT. See, what VBT tells us is that every metal atom and the ligand, the bond formed between them. Have you seen theory called hybridization? Yes, you have. You have seen the hybridization theory in organic chemistry, right? What does they have tell you is that the bond between your carbon and hydrogen is completely coordinate bond. Sorry, my bad. The bond between your carbon and hydrogen is formed by overlapping of orbitals between the two atoms. Same thing is also told by VBT. What does VBT tells? Is that the bond formed between metal and different ligand is purely covalent. There is an overlap. There is an overlap of atomic orbitals of metal and atomic orbitals of ligand, where the field, because ligands are bringing electrons, right? Where field orbitals of ligand are putting or donating their electrons into the empty orbitals of your metal atom, and metal atom makes available the empty orbital, so that ligands are able to donate those electrons into metal's empty orbital. Okay, and only those many numbers of metal's empty orbitals are available which are equal to the coordination number of your metal atom. Okay, because different metals have different coordination number. So that is what the VBT tells us, that the bond between metal and ligand is purely covalent. There is an overlap, okay, of atomic orbital between metal and ligand. So, and there is a hybridization. So there basically this theory is nothing but the one which we had seen in organic chemistry, hybridization. It is also hybridization, but this time it is of coordination compounds. It's a hybridization. Okay, so in this hybridization there are different kind of hybridization, obviously sp3, sp3d, sp3d2, sp3d3, sp3d4, sorry, not d4, sp3 d2 and sp3d3. So these are the different type of hybridization. Obviously and then they'll be arranged in a particular shape, okay, so that it would have some kind of geometry, okay, that we already know. So now VBT, so that is what the postulates of VBT are, okay. Now let's see its illustration straight away. Now CONH36Cl3, coordination number 6, okay. Now here see, hybridization is always shown by coordination sphere only. The compound which you have here, you need to dissociate it so as to have a coordination sphere, okay. Now I'll write it on this side. It ionizes to give you CONH3 6 3 plus 3Cl minus, okay. So basically cobalt's atomic number is how much? Cobalt's atomic number is 27. So its electronic configuration becomes argon 4s2 3d7, okay. But since the since the oxidation state is +3, that means it has lost 3 electrons. So CO3 plus, it would be what? It would be argon 4s0 and 3d6, okay. Now those empty orbital of S and the P which will be coming after this 4p0 can be utilized. They can be utilized for forming a bond, okay. How? Let's see. Now how cobalt makes this available, okay. Now I'm going to directly write about now I'm going to talk about these orbitals only, okay. Whatever we have on the left hand side, that is not useful for us, obviously. So let's see. So you have 3d6. How 6 electrons are arranged? Let's see. 1 2 3 4 5. 3d6, 4s0, 4p0. Electrons 1 2 3 4 5 and 6, okay. So you have empty s orbital and empty p orbital. Now see, we know that coordination number of cobalt is 6, right? And how many empty orbitals are there? There are only 4 empty orbitals, 1 in S and 3 in P. We need to make available 2 more extra empty orbital. Then and then only your cobalt can form a coordinate bond. Now the question is that extra orbital can also be available from 4d orbital also. 4d0, because that is also empty right now. 1 2 3 4 5, that is also empty. That 4d is also empty. Now the bond formation would form with 4d or not, that is actually not going to explain by VBT, that is going to explain by CFT. But okay, but before moving to that, I'm going to tell you what happens here. Okay, ammonia ligand is a strong field ligand. You would understand what is the meaning of strong field ligand and weak field ligand very shortly when we gonna see CFT, okay. But till then, let's understand this, that ammonia is a strong field ligand, and strong field ligand does what? It causes the pairing of this electron. It causes pairing of this electron. So this electrons gets paired like this. This electron comes here, okay, like that, and Oh, what am I doing here? Just a sec. Oh yeah, what is happening? Sorry. So other thing got also. Okay, now what happened here is the pairing of this electron happens. Now because of that, what happens? Let's see here. One, two, three, four, five, four. Okay, and as soon as the pairing happens here, you have these two orbitals available. Now, since you have these orbitals available, how many? 2d orbitals available, 1s and 4p. And this 6p orbital now undergoes hybridization. This 6p orbital, not 6p, sorry, this 6 orbital now undergoes hybridization. What is the name of that hybridization? These are D, these are S, these are P. Okay, and how many orbitals are there? 6 atomic orbitals are there. So because of which 6 hybrid orbitals would be formed. So basically this would give us 6 DSP2, sorry, 6 DSP, what I am saying, 6D2SP3, 6D2SP3 hybrid orbitals. One, two, three, 4, 5, 6. So every orbital here is D2SP3, 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 like that. Now your ligand will come, where each ligand will be bringing 2 electrons each. Each ligand will be bringing 2 electrons each. Where is ammonia? Ammonia ligand. NH3, 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 and each one of them is bringing 2 electrons each, and that is how this coordination sphere is going to form. And the shape of its what? Shape we as already know, it will be forming octahedral geometry. It would be forming octahedral geometry. Okay, that is how 6 ammonia ligands would donate their 12 electrons, 2 electrons each. Okay, and that is how you form this particular complex. Okay, you can take a look at it again for train of 15 seconds, or you can take a screenshot also. Okay, now that we had seen the coordination number 6 wala application of valence bond theory to coordination number 6, now let's see another coordination number 6. Okay, here. Now let me tell you one more thing here. The ammonia ligand that we took here, it was strong filled. It was a strong filled ligand. And what does strong field ligand do? it causes pairing of electrons. It causes pairing of electrons. You can take a look at it again. It causes the pairing of electron. That means weak filled ligand do not causes pairing. Only strong filled ligand causes the pairing of electrons. Okay. Now, ammonia ligand obviously is a strong filled ligand. That is why it causes pairing. So the next ligand is fluoride. Now let me tell you on the very first point is that fluoride is not a strong filled ligand. It's a weak filled ligand. So since it's a weak filled ligand, it do not causes any pairing whatsoever. Okay. Before moving to that, what is this compound? It will give you 3Na plus. That means this compound would be having coordination species will be having COF6 3 minus. Okay. And what is the oxidation state of your cobalt then? Oxidation state of cobalt is +3, right? And in the previous example only, we had seen the electronic configuration of cobalt in +3 become what? It becomes argon 3d6 4s0 4p0 4d0, right? We had seen that in the previous slide only. Okay, so how would it look like? Let's see now. Now I'm going to write each one of them having separate space. 3d6 4s0 4p0 4d0. Okay, so 3d6 1 2 3 4 5 4s0 4p0 and 4d0. Okay, now d6, how are you going to arrange the d6 electrons? See, they will be getting arranged like this: 1 2 3 4 5 and 6th electron will be here. Now as I told you earlier that ammonia causes the pairing of this electron. Okay, but fluoride F minus is a weak filled ligand, so it cannot cause the pairing of this electron. So since it cannot cause the pairing of this electron would stay as it is. But for fluoride to form a coordinate bond or to overlap with the cobalt's empty orbital, it is necessary that cobalt should have 6 empty orbital. So do they have an empty orbital from this orbital? No. Then what would it do? It would take the 4d orbital. Now 4d orbital is kind of a outside orbital or outer orbital, and that is why such a complexes are called, just a second. Okay, that is why such a complexes are called as outer orbital complexes. Outer orbital complexes. Why outer orbital complexes? Because it cannot cause a pairing of this d electron. So therefore, this d orbital remains fulfilled only, because of which only those orbitals can be utilized. Same thing did not happen in case of strong filled ligand like ammonia or cyanide. In those cases, it causes a pairing of this electron, so this became available. So that is why those were inner orbital complexes. For a weak filled ligand, it is a outer orbital complexes, and therefore now what will happen is that this one is 3p 2d will overlap to give you sp3 and 2d. This will give you 6 sp3d2 hybrid orbitals. This will give you 6 sp3d2 hybrid orbital. So now one, two, three, four, five, six. So these are 6 sp3d hybrid orbitals, and now each fluoride would come there. F, 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 F. Every fluoride has a negative charge. So every fluoride will now donate the lone pair. And that is how you get COF6 3 minus complex. That is how you get outer orbital complex by having weak filled ligands. Okay, take a look at it again. Okay, chalo. Now let's move to the next, coordination number 4. Now that we have understood how coordination number 6 shows two types of complexes, inner orbital and outer orbital. Now we're going to see how the coordination number 4 also shows two types of complexes. Okay. Now the first one is K2NiCN4. Now what would it give you? It would give you 2K plus NiCN4 2 minus. That will make nickel to have +2 oxidation state. How? Let's see now. Atomic number of nickel is 28. So its electronic configuration is argon 4s2 3d8. Right? 4s2 3d8. So now what will happen? Nickel is in a +2. Nickel +2. It would give you argon. 4s2 would be lost, and you would be having only d8. 3d8, 4s0. Sorry. It will be having 4s0. Okay, now how can we arrange it? Let's see for the bonding. One, two, three, four, five. That's 3d8, 4s0, which is empty obviously, and 4p0, that is also empty. Right? 4p0 is also empty. Now, how would you arrange these 8 electrons? See. Now, again you need to understand one point. Cyanide is what? Cyanide is strong filled ligand. Cyanide is strong filled ligand. Now here you need to understand which is a strong filled ligand, which is a weak filled ligand, which we're gonna see again in a CFT, crystal field theory. Okay, but for the time being, let's remember that halides are weak filled ligand, ammonia, cyanide, CO. Okay, these are strong field ligands. So now वैसे तो यहाँ पे 4 ऑर्बिटल अवेलेबल है. You can see S 1s and 3p orbitals are available there itself. Okay, so क्या कर सकते हैं हम लोग, वो तो अवेलेबल है तो अब तो बॉन्डिंग हो सकती है, लेकिन क्योंकि साइनाइड क्या है, स्ट्रॉन्ग फील्ड लिगैंड है. सो व्हाट वुड इट डू, it would cause this electron to get paired up here. It would cause that electron to get paired up, because of which now you would have what? You would have all the electrons in D as paired up. S का तो पहले से भी अवेलेबल था और P तो अवेलेबल है ही है. Okay, so now all the electrons are paired in a d orbital. So you have one d available, you have got one d available, one s available, and two p are available. Now we can take 2p only because we need 4 orbital. Okay, so now what will happen? So you would now have D, S and 2p. So that will give you 4 dsp2 hybrid orbital. It will give you 4 dsp2 hybrid orbital, which will be arranged in a square planar shape like this. That is how nickel and cyanide are bonded in a square planar fashion. Like this, NiCN4. That is how you form a inner orbital complex. Now here sp3 hybridization could have occurred, okay, but since this compound shows, I will tell you about magnetic property. See how magnetic property actually tells you the shape of the compound, because suppose had this compound given sp3 hybridization, then these electrons would have remained like this only, right? Because in that case it would have straightforwardly taken S and P, sp3 hybridization, right? So in that case these two electrons would have remained unpaired and compound would have shown magnetic moment. But as a matter of fact, this compound shows no magnetic moment whatsoever. So then people thought, okay, this compound does not show any magnetic moment. That means what must have happened is that this electron must have got paired with this. So as soon as it has got paired with this, you must have this available, and that 2p available. So which of, and then those must have combined to produce this square planar NiCN4 2 minus. Okay, you can again take a look at this. I'll just write it's the name of the geometry. You can take a look at it once again. Okay, so I hope this must have been clear to you. Now let's move to the next compound, last compound. Again, this compound also is having nickel in a +2 oxidation state and ICl4 2 minus, which makes nickel to have +2 oxidation state. And nickel in +2 oxidation state shows what? Argon 4s0 3d8, right? So now how would you write? Again 3d8. One more thing, 4p is 0, right? Yeah. Now we will write each one of them separately here. 3d8, 4s0, 4p0. Okay, now how would you arrange these electrons? Now you would be having 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. Right? Now comes the question, what happens now? Now I need to tell you one thing here is that chloride is just like fluoride, it is also weak field ligand. Okay, your chloride is weak field ligand. It is also weak field ligand. So since it's a weak field ligand, that means what? Since it's a weak field ligand, it will not cause the pairing of electron. Electron would stay as it is. So there is no pairing of this electron. That means this last d orbital is not going to get empty. That means you need to arrange 4 orbital. How are you going to arrange? Well, it is quite obvious is that this s and 3p orbitals, they are going to get combined, right? S and 3p, they are going to combine to give you 4sp3 hybrid orbitals. They are going to give you 4sp3 hybrid orbital, where your chloride ligand would come and would deposit their electrons to cause the pairing. That is how NiCl4 forms. And since it's a sp3, therefore NiCl4 would be showing the shape like this. Tetrahedral, as you already know the geometry. Right? NiCl4. That is how NiCl4 geometry is formed, and that is how the VBT theory is summarized to you. Anionic. Okay, chalo. Moving ahead now. Before we move to the magnetic properties, let me tell you one thing clearly. VBT has explained VBT has explained the compounds can be inner orbital, it can be outer orbital, and it has commented a little bit about magnetic properties. Okay, but VBT theory has lots of flaws. The very main flaw is that it could not explain why some compounds are forming outer orbital complexes, why some compounds are forming inner orbital complexes. That means it could not tell why the given, it could not tell why some compounds are strong field ligand, why some compounds are weak field ligand. That it could not tell, and that we're gonna see in a spectrochemical series, obviously. Okay, but as far as VBT is concerned, VBT could not tell us. Similarly, VBT could not tell the exact geometry. In some compound, geometry was seen to be perturbed. VBD could not explain that. So VBD could not explain the magnetic property, and lastly, VBD could not explain the spectral properties. That means why some compounds are colored, why some compounds are colorless. VBD could not explain that. Okay, that is a major point you need to consider while understanding what VBD has offered us. Okay, sure. Moving ahead. Now magnetic property. Now what I have written here, what is this? This is nothing but what is this? This is your Gauss balance. Gauss balance. And what does it do? What does it do? See, this is a sample container. This is counterweight. Okay, it's a balance. You know what balance is, right? Counter sample container. This is what? This is your sample, which obviously contains some substance. What are this? These are your magnets. These are your magnets. Okay. Now what happened here? See, as soon as you put compound into this sample container, if your sample or if your substance is happen to be paramagnetic, then this weight that you want to measure here, this weight seems to be increased. That means, suppose if you take a 1.2 gram of the compound, before you could put the compound into Gauss balance, its weight was 1.2 gram. Okay, in the normal balance obviously. Then you put the compound here in the Gauss balance, and what you found is that compound's weight seems to be increased. It is around 1.25 gram or 1.3 grams. Now why is that so? Why is that so? It's because whenever you have a paramagnetic compound here, what these magnets do is that paramagnetic compound gets attracted to the magnet. Basically, magnet attracts the paramagnetic substance. So as soon as it attracts this substance, this will get pulled down. So when this will get pulled down, the weight seems to get increased here. You know the mechanism of balance, right? When you pull this down, this weight seems to increase. When you push this up, this weight seems to decrease. Okay, so here, since if the compound is paramagnetic, it will get attracted towards this magnetic field, and this will get pulled downwards, which will show that weight has increased. And that is how people or us come to know that whether compound is paramagnetic or diamagnetic. Exact opposite happens if the compound is diamagnetic. If the compound is diamagnetic, what happened then? Then the weight seems to decrease. Suppose if you take a diamagnetic substance whose weight was 1.2 gram, okay, outside, I mean without this balance obviously, and when you put that into this balance, you found that its weight is 1.15 gram or 1.1 gram. Now weight seems to decrease. How? Because whenever you have a diamagnetic substance here, it will get repelled. It will get repelled by the magnetic field. Magnets repelled it. So when they repels it, it's like pushing this up. So when you're pushing this up, the weight seems to decrease on this counterweight. And that is how you come to know whether given compound is paramagnetic or diamagnetic. Okay. And there are some compound whose weight doesn't seems to change at all, neither decreases nor increases. So for those compound, what? Those are non-magnetic, obviously. Okay. So now, as far as this is concerned, the paramagnetic substances has what? Paramagnetic substances, they are having at least one unpaired electron. They are having at least one unpaired electron. Diamagnetic substance has 0 unpaired electron. They are having 0 unpaired electron. Okay. Now, if you are having 1 unpaired electron, 2 unpaired electron, 3 unpaired electron, then what could be your paramagnetic moment or magnetic moment for that matter? We had already seen that in a chapter called D block and A block. You can check it out in that. Okay, which was the very first chapter of our one-shot series, and I have made a separate video also on gauge balance. You can check that in same channel of where this video is going. Okay, chalo. So we'll not spend much time here. Now, anomaly with magnetic property. Let me tell you, there had been some anomaly with magnetic properties. For example, the compound called this compound MnCN5 Cl3, not actually Cl3, this compound only, MnCN5 2 minus CN5 2 minus. Here the oxidation state of manganese is +3. So if you look at the manganese atomic number is 25. So it's a argon 4s3d5, right? Now since manganese is in a +3, that means 2 electron from S and 1 electron from D has gone. So you have only 3d4. So 3d4 should have electron like this. Okay, and now as I told you, cyanide is a strong field ligand, so there must have been pairing of this electron, right? Now let's consider these two cases. Here you have a 4 unpaired electron, here you have a 0 unpaired electrons. Okay, so whenever you checked with Gauge balance, it should either show 4 unpaired electron or 0 unpaired electron. But let me tell you for your information, the Gauge balance tells us that this compound has 2 unpaired electrons. So in reality, it does not have 4 or 0, it has 2 unpaired electrons. How? We don't know. There is an exception, and that is where the name came anomaly. Okay, there are many such cases of anomaly. You can check that in book also. I'm just telling you or giving you a brief summary of it. Okay, chalo, moving ahead. Now limitations of VBT that we had already discussed, right? What were some of the limitations of VBT? VBT could not tell us why the particular compound forms inner orbital complex, why particular compound forms outer orbital complex. It could not tell us the spectral properties, magnetic properties. Okay, and do you remember the ionization isomerism? There only those compounds are able to show ionization isomerism for which the counter ion can also act as a ligand. Okay, now counter ion basically was acting, counter ion was acting as if it is forming an ionic bond with a central metal atom, but suddenly it involved in a coordinate bond with the metal atom. How? VBT could not explain that. That is why VBT theory, I'm not saying it was rejected, it was still useful, it is still worthy, okay, but it could not explain some properties, some magnetic property, some spectral property. Obviously spectral properties means color of the complexes. Okay, so now that is why we're going to move to the crystal field theory. This is the most celebrated theory. This crystal field theory is the most celebrated theory of coordination compound. Very, very highly celebrated. Why and how? Let's see now. So what crystal field theory does is that it considers a metal as a point charge. It considers metal as a cation and ligand as an anion. Now you would say, sir, not every ligand is an anion. Yeah, you're right. So it has considered the ligand with negative charge as an anion, which is obvious, and ligand with lone pair donating capability as a dipole. That means the part where ligand is donating electron density is negative part of a dipole, and be opposite to that there is a positive part of a dipole. Okay, so it has considered neutral ligand as having dipole and negatively charged ligand as an obviously anion, and metal as an ion. Okay, and this theory says that there is an electrostatic force of attraction. Now let's understand the difference very carefully. VBD has said that there is a covalent bond of or overlap of orbital between metal atom and ligand. Crystal field theory says there is no overlap. There is absolutely no overlap between metal atom and ligand. There is a pure electrostatic or ionic interaction. As you know, there is a pure electrostatic force of attraction or ionic interaction between the point charges. Which point charges? One is positive point charge, metal, and another is negative point charge or dipole wala point charge from ligand. And whenever this interaction happens, the ligand creates the electronic field. The ligand creates, suppose this is a metal atom. Okay, so ligand creates the electronic field around the metal atom or ion, and if this ligand field, this electronic field which has been created by ligand is also called as ligand field. That is why the name came, crystal field theory, field. Okay, so this ligand field, if it is a homogeneous or symmetrical, then the metal's d-electronic configuration stays as it is, or I would rather say it stays as degenerate. So let me tell you for your information that we know that d orbital, there are 5 types of d orbital, right? Let me write them one by one here. So these are 5 d orbital: dxy, dyz, dxz, dx square, dash y square, and dz square. This is called as what? This is called as degenerate orbitals. What is the meaning of degenerate orbitals? Degenerate orbital means the orbital whose energy level is at exact same level, like this. No orbital is above, no orbital is below. Okay, their energy level is at exact same level, and such orbitals are called as degenerate orbital. That is what a d orbital is. So this theory says that this d orbital stays degenerate only as soon as the ligand field comes and surrounds the metal atom. If that ligand field is symmetrical, then this degenerate orbital stays as degenerate only. Okay, but if the ligand field which is coming, if that ligand field is not symmetrical, if it is unsymmetrical, if that ligand field is unsymmetrical, it would cause the degeneracy to get removed. Basically, it breaks the degeneracy, and some d orbital will go higher up in the energy, some d orbital will go lower up in the energy, and that is what happens in a octahedral field. In octahedral field, what happens is that this here, just let me write it completely. Yes, now I can write it. Yeah, so here what has happened is that dx square dash y square and dz square, they goes up, and dxy, dyz and dxz, they comes down. And what is this? This is a central point. So as soon as the octahedral field, or let me write it here in a bold letters, octahedral field. As soon as the octahedral field comes from the ligand, it splits. The degeneracy option metal gets removed and the metal d orbital gets splits into two sets. One is dx squared dash y squared dz squared, which is also called as Eg, and this is called as T2G. What is the meaning of T2G? T stands for 3. Triply degenerate. Now let's look at here. These three orbitals are still degenerated. That means they are at the same level, right? So that's what T2G stands for, triply degenerate. Again, this Eg, these two orbitals are degenerate among themselves. Okay, if you are comparing them with other d orbitals, they are obviously in a different energy, but among themselves they are degenerate. So they are that is called as doubly degenerate. E stands for 2. Doubly degenerate. This is triply degenerate, and that is how the metals, d orbitals degeneracy gets removed, and what happened is that d orbital gets split up into two set of orbitals, Eg and T2G. Okay, so sure. Now let me tell you the whole game altogether. Okay, let's not stage it. I'm going to tell you the whole game here. Now let me tell you, whenever the ligand comes, as I told you, now you will understand why some ligands are strong field, why some ligands are weak field. Now let's understand this point. The ligands which are strong field, they does what? They cause this gap to be larger. The ligands which are strong field, for example, ammonia, carbonyl, cyanide, PPH3, this ligand does what? This ligand makes this gap bigger. They make this gap bigger. So whenever they make this gap bigger, what happens is that they basically cause a pairing of electron. How? Let me show you. Suppose the first electron comes here, 1. We're going to see it again, but I'm just giving you demo here. So first electron comes here, 1, 2, 3. 3 electrons have been distributed, right? Now the fourth electron. Now the fourth electron, would it go up here or would it get paired up here? Now that is decided by the ligand field. If the ligand is strong, this gap is bigger. When this gap is bigger, the fourth electron needs to go higher up in the energy. Let me tell you here, this energy, see, this is energy gap. Energy is increasing. So if the fourth electron has to go up here, it needs to absorb this much of energy, then and then only it can go up there. But since the gap is larger, it does not go that up. It prefers to stay paired up here only. So fourth electron gets paired up. Fifth electron, same thing happens with it also. D5, sixth electron also gets paired up, D6. That is why D1, D2, D3, D4, D5, D6, they get paired up. Now you got it? How the strong field, weak field actually was operating? Strong field ligand causes this gap to be bigger. So that is why the fourth, fifth and sixth electron, they cannot go higher up that much. So they prefers to pair up here only. Okay. Now the seventh electron, when the seventh electron comes, it has no option but to go there only. So it goes there. 8 electron goes here, 9 there, 10 there, like that. That is how this whole game of strong field and weak field ligand is all about. I hope this must have been pretty much clear to you now. Now, let's understand one more point here. That is for the higher up, as I told you. If the ligand is weak, for example, fluoride, chloride, bromide, iodide, water, these are the weak field ligand, right? So for the weak field ligand, what happened? This gap is not that bigger. This gap is not that bigger. So therefore, first 3 electrons are going to come here only, which is obvious. 1, 2, 3. Now the fourth electron can go up. Why? Because the gap is not bigger, gap is smaller. So fourth electron goes there, fifth electron goes there. Now you got it. Why? The weak field ligand does not causes a pairing, and those compounds tends to be more magnetic. Okay, so 1, 2, 3, 4, 5. Now the sixth electron come, it will start pairing. 6, 7, 8, 9, 10. Like that. I hope the picture is very much clear to you now. So now the question is, why is it so that dx square dash y square and dz square, this stays up, and dxy, dyz and dxz, they stays below? Why? It's because in octahedral field, what happened? See, ligands are approaching metal atoms or ion. Whenever they approach, then only there would be a creation of a electrostatic force of attraction, and then there will be a development of bond between them. Okay, but ligand has to approach metal atom or ion from certain direction. Okay, so as far as octahedral field is concerned, this is octahedral field. Octahedral field. So as far as octahedral field is concerned, the ligand approaches the metal atom from xy. Ligand approaches the metal atom from x and y axis and from the z axis. So we know how the electron density is distributed in d orbital. In dx square dash y square, it is along the x and y axis. X and y axis. These are the three axes: x, y, z. So in dx square dash y square, electron density is along the x and y axis. Now ligands in octahedral field are approaching these axes only. So ligands are bringing their electrons, right? And metals d electrons are also there, right? So now metals d electron and those ligands d orbital, and the ligands electrons, there is a repulsion, which is obvious. This is the ionic interaction. No, crystal field theory is all about ionic interaction. So metals d electrons density is along the x and y axis, and the ligand is also approaching the x and y axis. So therefore there is a strong repulsion between these two electrons that causes the potential energy to go up, and that is why dxy goes up. Same thing happened with dz square. In dz square, electron density is along the z axis, right? So now whenever the ligand approaches from the z axis, the electron density gets repelled, potential energy increases, and that is why it goes up. Same thing does not happen with these three orbitals. That is why they are down, this is up. Okay. Now as far as tetrahedral field is concerned, exact opposite happens. In tetrahedral field, this is tetrahedral. See, this is tetrahedral. Let me put this pen here. This is tetrahedral. Okay, like this. Now in tetrahedral, what happened is that ligand approaches along the xy, yz and xz axis only. That is why tetrahedral, the splitting of tetrahedral is exact opposite to the octahedral. Okay, exact opposite to it. And the tetrahedral field is weaker than octahedral field, which is obvious because tetrahedral has only 4 ligands. Octahedral has 6 ligands. So more the ligands, more is the repulsion, and stronger is the splitting. So that is what this representation was. Now you can quickly look at here. CFT, crystal field theory. Now see, d orbital Fe2 plus, and I was telling you, okay, it got split into T2G, Eg, right? Fe, oxidation state of Fe is how much? It's +2. Electronic configuration is argon 4s2 3d6. Okay, so this 2 electron goes, you are remain with d6, 6 electrons only, right? How are you going to arrange the 6 electron? 1, 2, 3. Now H2 is what? It's a weak field ligand. H2 is a weak field ligand. So what will happen? 1, 2, 3. 4th electron will go up. 4, 5, 6. Now pairing will happen. Clear? Right in front of you. Now look at the cyanide. In cyanide, see, right in front of you, this gap is smaller, this gap is larger, right? In cyanide, what will happen? 1, 2, 3, 6 electrons are there now. 1, 2, 3, 4, 5, 6, right? And upper one is empty only. That is how the CFT is all about. Okay, I hope this must have been pretty much. See, CFT can explain the magnetic properties, it can explain the shape and color of the complexes also. We're going to see it very soon. Okay, so you can take a look at it, you can take the screenshot of it also. Okay, sure. Moving ahead. Now see, this is a spectrochemical series. What does spectrochemical series do? Spectrochemical series will tell you which is a strong field and which is a weak field ligand. So you can see here, these are right on top. These 4. Remember always, amine, ethylene diamine, cyanide and carbonyl. These are strong field ligand. How it is been found out? We don't need to pay that much attention to it, but you need to understand that these are a strong field ligand and these are what? These are weak field ligands. Weak field ligand. All of this still here. These are moderate. NCS and NDTA, they are moderately weak, moderately strong field ligands. Okay, you already know what spectrochemical series is. It is in your book, right? So distribution of d electron. Now we're going to see how d electrons are distributed in a different d orbitals. Okay, strong field, weak field. Okay, this upper one is always what? Upper one is T2G always, remember. Sorry, upper one is EG. Sorry, my bad. Upper one is EG always. Okay. So I'm not gonna tell you the D1, D2 and D3. Why? Because you know it is same. Yeah, what is happening? See, D1, D2, D3, D9, D10. Remember or mark my words or listen to me carefully. D1, D2, D3, D9, D10. These 5 systems are exactly same. Be it a strong field, be it a weak field, doesn't matter. Okay. Now, and as far as tetrahedral is concerned, there is no strong field, there is no weak field. All of them are weak field only in tetrahedral, because tetrahedral ligands are 4 only, so it has to be weak field. Octahedral, 6 ligands are there, therefore ligands, therefore it's a strong and weak field. So now we're going to talk only and only about strong field ligand of octahedral. Sorry, strong and weak both of octahedral field only. Okay. Now let's see how the pairing is. Now we know that, see, D3, D4, D5. So as we already seen, 1, 2, 3, it will stay like this. See, in weak field also it is exactly the same. Okay, demo is right in front of you. Now D4, what will happen with D4? 1, 2, 3. So this is a strong field, so it will prefer to pair up here only. Here it's a 1, 2, 3. It's a weak field, right? So it will go out. Now with the D5, 1, 2, 3, 4, 5. Here 1, 2, 3, 4, 5. Look at it. Take a look at it again so that there would not be any confusion for you. Okay, chalo, you can take a screenshot. We can move ahead now. The next one. In the next one, it is again let me again write it. Strong field, weak field. Okay, we had seen D3, D4, D5, right? Just a sec, let me take a look at it. Yes, now we're gonna see D6, D7 and D8. D9, D10, as I told you, they are one and the same. Okay, so D6, 1, 2, 3, strong field now. So pairing 4, 5, 6, right? What will happen in the weak field? 1, 2, 3, 4, 5. Now the pairing will start. D6, D7, 1, 2, 3, 4, 5, 6, 7. Weak field 1, 2, 3. Always fill the electron in this fashion only, okay? So as to avoid the confusion. 1, 2, 3, 4, 5, 6, 7. Okay. Now let's look at the D8 so that your picture will be quite clear in front of you. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Just look at it. What do you see here? Is that D8 is exactly same for weak and strong field. Just look at it again. Or let me highlight it. Look at this. They are exactly same. That is what I was telling you. D1, D2, D3, D8, D9, D10. For all these 6 systems, be it a strong field or be it a weak field, the electronic distribution is exact same. The electronic distribution differs only for D4, D5, D6, D7. Okay, picture is right in front of you. You can take a look at it. Okay, chalo, moving ahead. Now the last point, in fact second last point, color in complexes. Now see, some d orbital shows color, sorry, some compound shows color, some compound do not show color. Now which compound shows color? See, you need to understand that only those d orbital only those complexes shows color which has at least one d electron. That means d0 and d10. D0, arey yaar, what is happening? Just a sec. Yeah, D0 and D10. D0 and D10 complexes. D0 and D10 complexes are they are what? They are colorless. They are completely colorless. They would not show any color whatsoever. Okay, D0, D10 complexes are colorless. So D1, D2, D3, D4, D5, D6, D7, D8, D9. This compound can show color, and they do show color. How? Well, that is what I'm going to tell you here. So the next part that we're going to see is color in complexes. See, many of the d orbital complexes or coordination complexes are colored. Okay, but for any compound to be colored, it should have at least one d electron. If it does not have that one d electron, it would never be colored. It would always be colorless. For example, see, you need to understand that D0 and D10, these systems are always colorless. They are always colorless. For example, take any compound of a zinc. For example, ZnH2O 6Cl2. Cl2. Your zinc is in a +2 oxidation state here. Okay, but this compound is colorless. Why? Because +2 means what? Atomic number of zinc is how much? Is 30. So electronic configuration become argon 4s2 3d10. So zinc +2, no? Zinc +2, that means this electron gone. So now you have what? You have argon 3d10. So it's a d10 system, right? So you should have at least one electron of d. Then and then only it would be. Now you might say, sir, d10 has 10 electrons. No. Yes, you are right. But see, you will understand very shortly why these d10 systems are not colorful. Because electrons should jump from T2G to EG. When, see, we had seen the splitting of d orbital, right? We had seen the splitting of d orbital into what? Into EG and T2G. This is your EG, this is your T2G, right? So this gap see, this is the energy difference, right? Your energy is going like this. So this is your energy gap. So this energy gap, see, there is a difference between the energy levels of EG and T2G. And you know that UV, ultraviolet, is also having some energy. Visible region also having some energy. Then IR, radio, all of these are also having some energy, right? But out of this whole spectrum, we are able to see only visible spectrum, right? So this energy level, this energy gap, or this energy level lies in visible region. It lies only and only in visible region. So what happened with any compound having one d electron? If the d electron is present in T2G, which is obviously present in T2G, from there it travels to EG. Okay, so whenever it goes from here to there, it absorbs some amount of energy. Some amount of energy from what? From white light spectrum. So whatever amount of light it absorbs from white light, okay, and whatever, see, white, we know that white light is composed of what? White light is composed of 7 different colors. We call that as Vibgyor, right? Violet, indigo, blue, green, yellow, orange and red. So whenever electron jumps from T2G to EG, it absorbs some part or some fraction of the white light, and whatever color that fraction is corresponding to, the complementary of that color would be seen as the color of that compound. For example, I'm going to explain this to you by using the color wheel, but for the now let's understood that whatever part, whatever light fraction, whatever frequency corresponding to particular color is absorbed by particular compound, the complementary of that color is seen as the color of this particular compound. Okay, now without wasting any time, let's check it out. I'm going to show you. See, look at this compound. Sorry, look at this color wheel. It is known as color wheel. This is called as color wheel. I'll write here rather. Color wheel. So I don't need to write that, but okay, I'm telling you. So what is this? This is violet. What is this? Blue. VIB, G, Y, yellow, orange, and red. Okay, all of this together. So firstly, what is happening? This is your white light. This is your white light. Okay, it is traveling like this. Okay, and your compound is here. Compound or your complex is here. Okay. Suppose out of, see, white light, we know that white light is composed of Vibgyor, violet, indigo, blue, green, yellow, orange, red. Okay, if suppose this complex is absorbing only this part of the spectrum, if your complex or your compound is absorbing this part of the spectrum only, then resultant, whatever fragment is remained, your compound would then show yellow color. If it is absorbing red part of the spectrum, it will look like green. If it is absorbing blue part of the spectrum, it would look like an orange. Just like that. It is that simple and straightforward. So let me take you one example. Scandium H2O6. Okay, so this compound here, your scandium atomic number is how much? 21. Its electronic configuration is argon 4s2 3d1. Okay, basically this compound actually is this. Okay, so the oxidation state of your scandium is +2. Okay, so basically these two electrons has gone and your scandium now has argon and 3d1 system only. Do you know what is the color of this compound? Let me tell you, but before let me take you to this. So this got 1 d electron. How are we going to distribute it? We know that we distribute this as T2G and EG, right? This is your T2G and this is your EG. Okay, so your single electron, it is present here. Now what happened? Whenever any form of a light falls on it, this particular electron absorbs yellow part of white light. So by absorbing yellow part of a light, it goes from there to here. It goes from there to here, and that is why whatever light which is coming out from there to here, it is looking like a violet color compound. You might say, sir, why didn't you write with the violet font? Because that might not be visible for you. Red color is quite visible. So the given compound is violet colored compound. Why? Remember, the color will, when it absorbs the yellow part of the fraction, when a yellow part of the spectrum, it will look like a violet, and so on. That is how this particular compound looks like a violet color compound. So that is how the whole chemistry of color in complexes is all about. So take a look at it once again. Okay, so moving to the next part is bonding in carbonyls. Now, why are we see, there are different types of ligands, but why are we taking only carbonyl as a ligand as a special case? Because it is a special. Okay, I'm going to tell you very shortly why. Before that, let's look at this nickel carbonyl NiCO4. This is NiCO4, which is tetrahedral in shape, FeCO5, trigonal, bipyramidal, CrCO6, octahedral, and all that. You can see all of this. But I'm going to tell you the specific point that is special in a carbonyl complexes. Let's see how. See, what happens in bonding in carbonyl is that, see, this is your metal, okay, and this is where your carbonyl is. C triple bond O. Okay. Now what happened? Your carbon is having a lone pair here. Okay, this lone pair is donated to your metal, and what does that form? That forms sigma bond. It forms sigma bond. So whenever ligand donates electron to your metal, it forms a metal ligand sigma bond. Okay, so this is the one way of forming a bond. What is the another way of forming a bond is that if your metal is rich in electron density, then your metal also donates electron density. It also donates electron density to your carbonyl. And that is what? That is your pi bond. That is pi bond. So this is whenever metal donates electron density to your ligand, that is your pi bond. And both of these type of bond, where ligand donating electron density to your metal and metal donating electron density to your ligand, both of these things, these two things happens synergetically. Basically, there is a synergism. Among these two factors. That is why metal and carbonyl complexes, or I would rather say carbonyl complexes, are very, very, very strong. Carbonyl complexes are extremely strong complexes. That's the reason for metal carbonyl to be studied extensively. Okay, sure. Moving ahead. Now the last part of this session is application of coordination complexes. See, coordination complexes has been used very widely. Some applications I have taken here, some applications I haven't taken because no need to. You can read it out also. See, many of the complexes of coordination complexes are used in a photography also. Okay, in photography you use different complexes. Similarly, hardness of water is estimated by complexing sodium and potassium cations in water with EDTA. EDTA can also be used in a chelation therapy. Your EDTA can also be used in chelation therapy, where it is used to remove or to chelate the mercury or cadmium or sometimes lead also from your blood if there is a poisoning of those elements. Okay, you can read it out. There are many applications of it. Okay, chalo. So that's it for this session. Do join us for more such videos. Okay, where we're gonna bringing more and more such videos in a one shot. Then you have a YouTube short also. Okay, for that, please check out our channel called Practically 11 and 12. Thank you.
Bring learning alive, practically.